Okay, so I would like to start by giving you some conceptual guidelines somehow. They are driving the research in this field. And I kind of like thinking this way, like as a more philosophical take. And then we're going to go into the definition. So the first peculiar aspect of this approach is the following one. So usually, if you study any theory of geometry, usually the theory starts with a model of geometric space. They tell you what a geometric space looks like. They describe that model in a specific way, and when they have the model, they develop geometry out of that. So that they develop some constructions that behave, or that comes out from that model. In particular, they, for example, define what the tangent bundle is, or other constructions. Like, you can start, for example, with manifold or schemes if you want to do algebraic geometry. Then you construct things out of them. Tangent categories are literally the opposite way. So you follow like a tangent-first approach. You start with an abstract notion of the tangent bundle. We have a collection of objects. Those objects they should be regarded as like abstract geometric spaces. We don't have a concrete description of those spaces. And we know that they carry a coherent notion of the tangent bundle. That's like the primitive data. And out of that, we interpret those objects geometrically. And we do other construction of them. Somehow, like, the tangent-first approach really focuses on the tangent bundle. Okay. Another take that I would like to give you is that for tangent categories, geometry is contextual. And the context that describes geometry is the tangent structure. So, for example, like if you have notions like local linearity, I'm going to talk about that. Those notions depend on the tangent structures. If you change the tangent structure, you have a different notion of local linearity. So we don't have intrinsic notions like, if you study linear algebra, you have what linearity means because you have like it's a map between vector spaces. That will be more like an intrinsic notion. In this case, the notion of linearity depends on the context. The context is given by the tangent structure. Appreciate what you have. So there are other ways to do differential geometry categorically. And one way is using SDG. SDG stands for synthetic differential geometry. In that approach, what they do is that they take the category of smooth manifolds and they make it nicer. So if you study category theory, usually you're quite picky about how the category behaves. You want to, for example, have limits and so on. And unfortunately, smooth manifolds don't have a lot of nice things that you would like to work with in category theory. In particular, for example, you don't have pullbacks. You don't have all the pullbacks. So what they do is to take the category of smooth manifolds and make it larger and nicer. But this has the cost of doing that is that this means that you might have some objects that are not as nice as smooth manifolds. You have things that are a little bit more pathological on the objects. So you have a nicer category, but you're losing on the objects. Tangent category is really the opposite. We are very minimal. We don't make things nicer. We take what we have. We work on the category of smooth manifolds directly. This is a bit of like a deeper concept. So before I show you a picture of the world of differential categories, one of those monsters is a CDC. CDC stands for Cartesian differential category. Can you understand my handwriting? I hope so. I'm not going to change that. So, so the idea of a CDC is to give you a contextual, a categorical context for multivariable differential calculus. Now, what you do in multivariable differential calculus, you think of things that goes from Rn, right, to Rm. These will be the objects. You have smooth maps between these spaces. Okay? And in a CDC, we have a way to differentiate those maps. So for every f that goes from A to B, we get a df that we call the differential of f that goes from A times A into B. So the idea is that df should represent the linear approximation of F.
Because the camera.
You can sort of catch the camera.
I see.
We catch one.
Oh, there we go. Yeah, good. Now it's fine.
Don't move to the left.
So you can move a little bit to the
So
left.
you can go like here.
Oh, I
No,
see.
the problem is that it switches
If
to
you
that
move to the
white.
left, good now.
No, but it won't switch until. I think it'll.
So myself, I don't have to go there. I see.
Yeah.
Okay, so let me stay this one.
Yes.
So okay. So if we have a fun,
I wanted to lock the camera on the board.
that's okay. So SCDC, if we have an F, we always get a DF. What is the interpretation here? So DF takes a point, a vector, and it sends to DF XV. The idea is that we interpret this as the derivative, the directional derivative of F along V, along the direction of V at X. Now notice one thing here. We're taking X in A as a point, but very importantly, V is also in A, but it's a vector. So the idea here is that the spaces here have this interesting property where points and vectors are somehow interchangeable. This happens specifically every time you have something like Rn. If you think of, for example, the plane, if you take a point, you can always see it to that point. Here going to be the 0, the unique vector that points to that point. And if you take a vector, well, you get the end point, right? But this is not true in general for other types of geometry. Like if you have like a sphere. Now, vectors belong to the tangent space, but clearly the tangent vector does not belong to the sphere. So the idea of tangent calculus is to say, if we want to include objects like this, we don't want to have only Rn or Rm. We need to separate between points and vectors. And the idea is that if you take that to the stream. So in particular, I'm not going to say that completely, but the idea is that points belong to the base object M. And we have a new space that also has points, but the points of this space are the vectors of M. So this way, points live here, vectors live there. So we have very distinct frameworks for points and vectors. So if I come back, can I go back to the slides? Thank you. So if I now go back to this like conceptual idea, one approach to do geometry with tangent calculus is to keep separating points and vectors. So in some sense, geometry happens when you separate points from vectors. That's kind of the catchy sentence I want to make. Against fiber bundles. Now, if you ever study differential geometry, by the way, my background is in physics. So I study theoretical physics and mathematical physics. And at some point, I got really interested in differential geometry because I wanted to understand GR. And I really liked it, but it's clear when you study differential geometry, and I hope I'm not offending anyone to say that, it's not an easy subject, it's quite heavy. You have a lot of structure. Like the first definition, if you start if you go on a course in differential geometry, you want to study smooth manifolds. But before you arrive to the definition of smooth manifolds, it takes at least a week to define it, because you have a lot of assumptions and so on. One of the core structures in differential geometry is this idea of fiber bundles. The idea is that if you think about points and vectors, in Rn, our vectors and points are interchangeable. In a sphere, they're not interchangeable. However, locally, you can still talk about points and vectors. So even if globally, you don't have a global separation between points and vectors anymore, locally, you can still do it. And this idea is captured by fiber bundles. I don't want to go into the theory of fiber bundles. What I'm trying to say is that we completely forget about that entirely. It's quite a heavy structure to have, and it relies on topological assumptions. And the idea is that in a tangent calculus, we don't think about it in that way. We completely eliminate all that structure. Remember that the idea of a tangent calculus is to have the minimal axioms, the minimal structures that we need to do geometry. And we do believe that having fiber bundles would be very nice in some context, but it's maybe not necessary to have a theory of geometry. So the advantage of that is that maybe we lose a little bit on the geometric interpretation of things. We gain simplicity in the theory. And in particular, we get a framework that applies in more scenarios. Okay, real numbers are not real. What do I mean with that? So when I studied differential geometry, I was really fascinated about the structures of differential geometry. And I really got convinced that you cannot do geometry without real numbers. Because differential geometry is all about derivatives and vectors. And how can you really say that something is infinitesimally close to something else if you don't have real numbers, right? So when I read the first time a paper on tangent categories, I got really surprised that they could say something about geometry without including anything that looked like real numbers. And it's actually quite fascinating, the fact that in a tangent category we don't assume the existence of anything that looks like real numbers. However, there's a paper where they essentially showed how to construct in a tangent category a special type of object called curve object. And a curve object is like the tangent category equivalent of a real number, real line object, sorry. So in some sense, the tangent category is still able to capture real numbers in a hidden way. So again, it's quite incredible that we can do a lot of constructions, geometric constructions, without talking about those things that seems quite fundamental. The final thought that I want to make before I start to do something a little bit more serious is to say that, to remember that a theory is not supposed to capture everything. We don't want to capture everything about differential geometry, neither about algebraic geometry, nor any other type of geometry. Why is that? Well, from a logical point of view, you can think of tangent categories as a theory. And differential geometry, algebraic geometry, non-computer geometry, models of this theory. Okay, so each model will have some special properties that depend on the model you're choosing of your spaces, and of course the whole theory will not capture that. The advantage of doing that, developing a theory, is that maybe the same structure can be replicated just one time. You can study that structure only one time, and then you have it in all the possible models. Also, I want to say that, at least from my point of view, I don't see tangent categories as trying to take over differential geometry or algebraic geometry. I don't think that's the goal. It's more to try to understand what is the theory behind all those constructions in some sense. So I kind of have to start planning a little bit what we're going to talk. So today I would like to give you a definition of a tangent category. It seems quite reasonable to do that. And after I build up the definition, I would like to talk about some examples. And in particular, I would like to show you this example where we're going to show that the category of fine schemes is itself a tangent category. We can do something geometric there. Next, I'm going to show you three important constructions that we have in tangent categories: vector fields and the early algebra, differential objects, and differential bundles. Now, maybe vector fields, you might have heard about that. Differential objects, differential bundles are the analog of Euclidean spaces and vector bundles in differential geometry. And these three are maybe the more fundamental construction that we have in tangent categories. Now, I'm not sure how much time we will have, but so this is literature. I kind of like to tell you something that I've done too, and hopefully I will able to have some time to talk a little bit maybe about my PhD thesis, where essentially I try to use tangent categories to develop a theory of operatic affine schemes. So the idea is that affine schemes are, the objects can be understood as the some type of rings, essentially. You can change that type of algebraic structure, maybe looking for Lie algebras or something like that. And so in that case, you will have operatic affine schemes. And the idea is that can we somehow do a similar construction using tangent categories? Okay, so the definition of tangent category requires a bit of it requires some structure. So I would like to don't give you the whole definition right away, but build up the definition. Maybe I can clear here. So the first thing I'm going to tell you is that a tangent category is a category. So I'm going to assume that, I hope I can assume that people knows what a category is. And can we be okay with that? Yeah. So, but maybe I can give you a little bit of the interpretation of that category. So the category remember that the goal is to say that the tangent structure gives us an interpretation, a geometric interpretation for the objects and for the morphisms. So let's try to understand what that means. So the category is given by a collection of objects, M and N, and I want that you see N as generalized geometric spaces. This, of course, is not a definition. It's not a formal definition. It's just an idea. It's just an intuition. Okay. So, like something where you can talk about, I'm inside. You can think of this like a spaces of points, and you're moving inside of those points, and you do things in there. So as a notation, you can think of this as a, pictorial notation. We can think about something like points, generalized points in M. Of course, this makes no sense in category theory in general, but like keep that in mind as an interpretation. Those geometric spaces have, though, an important property that are locally linear. I will try to explain as much as I can this concept, but the idea is that at every point, we can approximate that point with that space with something simpler. Okay, so when you study calculus, essentially what you do is that you're taking a complicated function, right? But if the function is nice enough, even if it's complicated globally, you still have that locally. It looks like something simple, like a polynomial thing, maybe a first-order polynomial, right? Those spaces have the same concept. Maybe the spaces can be incredibly complicated stuff with a complicated geometry, but if you zoom in enough, those look simple. They exhibit a local behavior. The maps between the spaces, the dimorphisms, should be understood as smooth maps. What does it mean, smooth maps? Maps that we locally approximated as linear stuff. For example, this function here. Okay, so that's what the category would be, and that's the interpretation that we somehow would like to give to this category, the elements of this category. So the next step is to introduce the tangent bundle functor. Tangent bundle functor. So here's the first idea. So as I said before, we would like to keep points and vectors separated. So the idea is that for every object M, we're going to assign a new object that we're going to call Tm. Tm is called the tangent bundle of M. So what is the idea here? The tangent bundle tells us what are the allowed directions that we can have in our space. So you can think of like you're sitting on a point, you look around, and the Tm tells you in what direction you can move from that space. So the idea is that you can think of this in the following way. You have your M, a point, and at every point, you have an associated spaces of directions, allowed directions from that point. So you can think of this something like this. If you have a background in physics, maybe you would like to say something a bit different. You would say that the points in M are positions. Well, those directions here, those vectors here, are velocities. Somehow, the tangent bundle contains all of them for every possible point. So this is the space of directions of allowed directions from that point. At this point, I also have the space of direction that looks like this. if you haven't done any differential geometry before, you might guess that this will be the tangent space essentially. So in TM, we are taking all the possible out directions in one single space. So currently, you think of the elements of T of M as pairs x and u, where x is in M, and u is a what I'm going to call a tangent vector of M at x. When I say tangent vector, is the same as velocity or direction with a speed, with intensity. Okay, so here I'm saying tangent bundle, and I'm also saying functor here. Now, apparently I cannot say you can use the word functor, but bear with me. So the idea is that, in a category, we don't just have objects, we also have morphisms. Here we have an operation that sends an object to another object of the same category. So somehow, we're going to say that T is something that goes from X to X. But clearly here I also have morphisms. So I have to say what this thing does on morphisms. Luckily, we have that every f, the interpretation that every f is smooth. So we can approximate it linearly. The idea is that for every f, from M to M, I get a T of N, of T of F, that goes from T of M to T of N. So how can we interpret that pointwise? So this sends X and U to F of X, df X. Here. The idea is that, this is the same notation that I used before for a CDC. This will be this linear approximation of f at x applied to u. Okay, so maybe I can start drawing some better picture here, better pictures. I love the fact that you have so much in mind, but it's great.
Thank you. So this, if I'm thinking back about the what you showed us with the A times A, why do we have this TM instead of having
M times M.
well, not M times A, but M times sums? Like, why do we not just define the directions and then take the product?
So that's the approach of a GCDC. So in the diagram that I showed you before about differential categories, we have CDC, we have DF that goes from A times A into B.
Marcello, can we ask you that when you switch boards,
I
in
see.
the beginning, don't stand in the border. First,
Okay, so the board is a problem.
yeah,
No, it's not a problem.
Continue.
You just first go to the middle and then you can.
Just look on that thing at times just to see if it's picking you up.
Okay, sure. So in a CDC, differential combination is defined as follows. In a GCDC, DF is kind of similar, but now we have A times L of A into L of B. L of A, you can think of this as as the space of directions of A. But when you say this, you're saying that every point, you're not saying that every point has a specific space of directions. You're saying that the space of directions is global. Every point has the same space of direction. Because you're splitting, you can split here between points and vectors. So here, points and vectors belong to the same space. Here, points and vectors belong to the separate spaces, but you can still split them globally. In a tangent category, we take that to the extreme. The idea is that not just we cannot separate between points and vectors, but also we cannot split them globally. And that is very important because if you do, for example, if you consider a sphere, in a sphere, the tangent bundle is never be written as, the tangent bundle of the sphere is not isomorphic to S2 times something else. That is not true. And it's because exactly there are some topological constraints that makes that. Like if you ever heard about the Hairy-Ball theorem, that's exactly what it tells you, a little bit more.
Maybe say some more words on that. I think Carlisle will appreciate
the plane. Why not?
Say some more, just mention the hairy ball.
Locally, it is.
I can do that, sure. So I mean, this is a bit of like a picture thing, but the idea is that you somehow, if you want to do this, it's the same as somehow as taking
Trying to comb the hair on a ball.
Yeah, so the idea is that like the tangent vectors, you can think of this as hair, right? Like this, and you do that at every point, right? But to do that, you want to somehow construct that construction. So you can start with like a ball that looks like this. Imagine like a like hairy board that goes like this, and then you try to like comb the ball. And there's an important theorem of algebraic topology that tells you that you can never do that. Like if you do that, at least one of the points has to be zero. Like there's no way to fully do that, which is the reason why I have the rows in my hand here. So it's the same problem, and because of that, this gives you a topological constraint on this. So this cannot be done. So the general theory of if you want to do that, considering that type of geometric space, you not just cannot separate points and vectors globally, but you would you can do locally, but you cannot do it globally. So when I write x and u here, this should be really understood as a point in the space, not as a global factorization of Tm. Is that clear at this point? I hope I'm making clear that.
If you could factorize it, then you could comb the hair on a ball.
Exactly, that's kind of the idea. So there's the idea is that we cannot say for every space that we have the space of direction is the same for every point. Okay. So what I was going to say, so tangent functor. So the picture here goes as follows. So we have, you can think of this as like your m. Here we have the t of m. And this is just a picture. We have an n. Here we have a t of n. This is a picture, but the idea is that here I have points, also here I have points, but here the points are the tangent vectors over here. So a tangent vector here corresponds to a point over here. Okay, and similar over here. So I have this one here, I have this, and this will correspond to a point over here. So to have a functor, it means that a point x is sent to f of x. This will be my f. And I also have a t of f, which means that now I'm taking a u. This u has to go on a tangent vector on f of x. That will be df x u. Okay? That's what the tangent functor does. Now, again, if you ever studied category theory, you know that a functor is not just an assignment, it has some properties. In particular, in a category we have identities and we have composition, and we want to have compatibility between these two operations. So in particular, t to the identity is going to be equal to the identity of t. So let's introduce a bit of notation. So let me write df xu. This is just a notation, okay? As in the following way: times u. Yeah? That's a notation. But this makes a little bit more clear what I'm doing, maybe. So if you do that, it means that you're sending. So the identity can be written like as a function takes an x and sends to x, right? It's just a function x somehow. So t to the identity takes x and u, and it has to send this one here to identity of x, identity applied to x, and then we have the notation, so dx times u. Okay, so forcing this one here to be the identity on tm, it means that this sends this one here to just the identity, right? So it's just xu. But this is going to be just x because it's just identity. So what we're really saying is that dx equal to u. We're saying that the derivative of the identity is 1 in some fancy way. We also have composition, right? So we have a way to compose two things together. So if you have an f, if I have an m, an n, and a p, f and a g, I want to be sure that if I do t of f, then followed by t of g, the same as composing them together. G composed with F, and T of G composed with F. Let's try to understand what that means with this notation. So T of GF takes XU and it sends this one here to G of F of X. Here we have the derivative of G composed with F in Y, in X, sorry, in X dot U. Can you guess what I'm going to use?
Chain rule.
Chain rule, exactly. So the functionality corresponds exactly to chain rule. So I'm going to show you that. So I'm going to do T of G composed with T of F of XU. So let me compose this here first. I'm going to have T of G of F of X. And here I have T of F dx dot U. Right? So now I'm going to do this, but this is going to be G of F of X. Here I'm going to do dg dy evaluated where? In F of X times this one here. But to have these two equal, it means that we have this equation. So dg dx must be equal to this thing. So the idea is that the functionality of the tangent functor tells us that the derivative of the identity must be equal to 1, and we want to have the chain rule for this like linear approximation of the functions. Okay, so we're starting to see that there's some like differentiability here going on clearly. Any questions on this?
We start with category and we have this functor. We require that we have the functor. That's part of the axiom.
Yeah, so the part of the axiom for now, we have a category, we have an end of functor on the category. But so far, I've been using a notation, I've introduced a notation, but I haven't justified the notation. So far, I just told you that's what it should look like. But now I have to give you the structure, enough structure to justify that notation. So I want to, again, I want to interpret the objects of the tangent category as locally linear spaces. That's what really tells me that I can use that notation for T of M and also for the F that stands in something like this. I haven't done that yet. I'm using the notation without justifying this amount. So the idea is that I need to add enough structures to make these an alleged tangent bundle functor. Or not just a functor, essentially. Okay, so what can I do? The first thing we're going to introduce is the additive structure. So additive structure. Okay, so the first thing we want to do is that if I have my T of M here, and here I have an M, I want to somehow have a way to forget about the direction here. So I'm taking a direction at a point. So a point here corresponds to a point plus direction. I want to send this point to its base point. I'm going to call this one here P of M. Oh, again, sorry. It's a very nice spot here, though.
I think you can probably stand there, but only after if you move to the middle first, then you can probably stand there afterwards. It just needs to know to.
I see. Yeah. Okay, so the idea is that I wanna have a way to forget about the direction and send every direction to its base point. So P is going to be called the projection. And if I want to use that notation, P takes an X and a U, and it sends to X. Okay, so far we just essentially have a way to describe. So for example, like, you know, if the fiber, I'm gonna say that many times, but the fiber is gonna be the pre-images of P. So if you think about this as like the pre-image of a point, it's gonna be this the directions that have as a base point X. So are exactly the directions that I'm allowed from X. So this way of doing things helps because instead of having a way to say, okay, for every point, I have a spatial direction, right? And for this point here, I have another spatial direction. I have to collect all those spatial directions somehow and put in the direction all together. And then I can use the idea of pre-images to talk about those spaces specifically. They're called fibers of the tangent bundle. Okay. Okay, so the next thing you want to do is to be able to have some algebraic operation for tangent vectors. So first of all, I want to have a zero tangent vector. So zero vector field. So we have projection, zero vector field. So zero vector field is going to say that at every point, I always have at least one direction, the trivial direction. The direction that tells me you stay here forever. Okay? So for every point x, I want to have a way to say, I want to associate to this x an x and a zero of x. A zero of x will be the trivial direction. How can I do that? Well, I have to define a map that goes from M to T of M. But a map like this, I take an x into, well, a y and a u. I want to force this y to be equal to x. So how can I do that? Any idea?
You compose the
Is that okay if I ask questions, by the way? Sorry.
Yeah, it's
I don't want to feel patronizing. I'm just asking to try to keep you alive, I guess. No.
and it'll be even better if students answer instead of.
So what would you do?
it's a student answer.
You can compose with the PM.
Yeah, right? And I'm going to say that it's going to be equal, right? So I'm saying that this is a section of the projection. The section of the projection is an assignment at every point of a tangent vector over there. This is what is called a vector field. And we're saying that there's always at least one vector field. There's two vector field. Okay. Next, we're going to be able to say, if I'm moving in this direction here, from this point here, and I'm moving from this point to this direction here, I somehow would like to be able to have a way to say, I can move to the directions at the same time. And if I do that, I essentially have to sum them together like this. So, this is the type of pictures. I want to move them like this, I can probably go like that. So when I have a way to sum vectors together. But be careful because I cannot sum two tangent vectors if I have a tangent vector from this point and a tangent vector from that point. I only would like to be able to sum vectors at the same base point. So I want to do an S that goes from T2M to T of M. What is T2M? So the interpretation of T2M should be something like a point, a vector at x, and another vector at x. So does anyone have any idea on how can we construct that T2M? So let me do first of all like this, the stupid thing. So I would take Tm times Tm. But Tm times Tm, I have xu and yv. The problem is that I have x and u, x and v, x and y, sorry, it can be different. And I don't want to have that. So how would you do, if you have any idea, how would you define this T2M?
Fiber product?
Fiber product, that's exactly it. So I don't call it the fiber product, we call it pullback. I would call it pullback. The idea is that we're going to use some universal property here. We're going to take P of M, we're going to take P of M, and we're going to take a pullback of P of M itself. The pullback is defined as follows. We have a pi 1 and a pi 2. And the idea is that,
So I guess we're assuming this exists also.
sorry?
I guess we're also assuming this exists, since you say not all.
We're gonna assume those pullbacks exist. That's right. We're gonna be very careful on what pullbacks we're gonna assume because again, man doesn't have all the pullbacks, but this is definitely one that we really want to have. Okay, so the idea here is that you can think of this in this following way. So here this contains x and u, this contains an y and a v. Here contains x, u, a y, and a v, satisfying the following condition. Pm of xu must be equal to Pm yv. But this is just equal to x, plus this is just equal to y. So in some sense, like a product plus a quotient. You're like no quotient, you impose a relation to that. You impose an equation. So I'm not sure how Are you familiar with the notion of pullback? Sorry, are we okay with that? Okay. Okay, so the sum then goes from the pullback of P along itself into T of M. And to answer your question more precisely, we're actually going to assume that all the n-fold pullbacks of PM along itself exist. And moreover, we're going to assume that the tangent bundle functor preserves these pullbacks. Okay, this is a technical assumption, but we're going to do that. Okay, so now we have a zero, we have a sum, and we have a projection. We're going to require that these form an additive bundle. So definition, an additive bundle in a category, this is not part of the definitions, in category X is the following data. We have a Q from E to M, we have a Z from M to E, and we have a sum from E to E where we're assuming the n-fold pullback to exist, and the sum goes from E to E. And moreover, essentially, I'm not going to write that down, but we have essentially unitality, associativity, and commutativity.
Wait, what are E and M here?
Sorry, what?
What are E and M?
Here I'm just defining what an additive bundle is in general.
E and M objects in X.
Exactly. E and M are objects in X, and Q and ZQ and SQ are maps in X. And I'm saying an additive bundle is this type of thing, such that it satisfies unitality, associativity, and commutativity, plus compatibility with the projection. So the idea is that, so if I come back over here, so what I'm going to say is that P, Z, and S are an additive bundle. So here the interpretation is that Z send X to X0 at X. The sum is going to take X, U, and B, and it sends to X, U plus B. So what I'm saying is that that plus is unital with respect to this zero, and it's associative and commutative. Okay? That's what it means.
So, but importantly, you want the X on the right-hand side to be X. So, I mean, just write that down as well, because you're not allowed to change the base point, right?
Yes, we're going to essentially ask also that if you project down, the same as taking P1, P. That would be also the other condition. And same for, this is going to be the same over here. Yeah. So I think I'm going to let you read my notes about this. And I don't want to do the whole definition, but the idea is that essentially we have the whole idea of this construction here is to say that if I take a point in my space and I'm looking at the fiber, so like the things that stay above that point, that form a commutative monoid. We can actually make precise that idea following lemma. Lemma? Additive bundle Q from E to M. I'm going to write this one here for those three maps. Okay. Is the same, is equivalent to a commutative monoid, in the slice. So do you know, does anyone know, doesn't know who the slice is? What the slice is? So let me say this. So this slice is the category whose objects are morphisms in X that ends up all the time in M, and morphisms F from Q to Q prime correspond to morphism from E to E prime that commute with E projections. Now the idea is that a product in the slice is a pullback in the base category. And so the idea is that if you want to define a commutative bond with respect to the product in here, it's exactly the same as an additive bundle in the base category. So this is actually something very important because I told you that an additive bundle, intuitively speaking, is like it's a bundle where the fibers are commutative monoids. To look at the fibers, another way to do that is to take the slice, because in the slice this becomes a commutative monoid. So I'm gonna stress that maybe later. Do we have any questions on this?
Just to be sure, this S sub M from T2 to TM, that's additional structure.
Yes. So for now we have a category, an end of functor T, projection, a zero, and a sum.
Oh, and obviously, I guess this additive structure must be preserved by the differentials.
Sorry, what?
The additive structure needs to be preserved by D, I guess, right?
So that preserved by D is naturality of this.
Okay.
So we're
Yeah,
going to say that those maps are natural. So I spelled a little bit more details on that in the notes, but the idea is that saying that it is natural is exactly to say that T of T of F, so this will correspond, the naturality of the zero will be df dx times 0 equals 0, and df applied to u plus v equals to df dxu plus df dx times v. So this is the naturality. This corresponds to the naturality of the zero. This corresponds to the naturality of the sum. And the naturality of the projection is what really tells me that that T of f of xu, the first component of this will definitely be f of x. I don't know what it is, but from here I definitely know that this will be f of x. It's the naturality of p. Okay, so far we introduced the additive structure. This is a very algebraic structure. It tells us that we can sum vectors together. We have a zero. Notice that I haven't required for a negative. We don't have negatives in a tangent category necessarily. However, sometimes we ask for them. In that case, we call the tangent category with negatives. So if you have negatives, to say that we have a map N that goes from T of M to T of M, it's also going to be natural. And the interpretation here is that you take ux into xu into x minus u. So in particular, this makes that commutative monoid into an abelian group. Or fiber-wise, the fibers will be abelian groups. Okay. So for now, we just introduced the algebraic structure of the tangent model functor, but that's not yet a tangent model functor. The hardest thing we need to introduce is the idea of local linearity. We haven't put that in yet. For now, we have this algebraic nice structure on the fibers, on the directions, on the space of directions. That's the one thing that I don't know if you ever study any differential geometry, but if you study differential geometry, you know that the space of directions are not just like commutative monoids or abelian groups. They're actually usually R vector spaces, where R is just real numbers. And as I said before, we don't have real numbers in a tangent category. So that part somehow coming from the local linearity I'm going to talk about later. Yeah. What time is it right now?
3. 3:05. Might be a good time for a 5-minute break if you were planning to have a break.
3:05. Okay, yeah. Okay, maybe have a little break and then we can maybe come back to second part. Or you can even forget about that, yes. Okay. We do that. Okay, so now I'm going to tell you about this local linearity assumption that we would like to put in. So what we would like to do is to say that the objects isms of the tangent category are locally linear. So we have two terms. We're going to see these terms once at a time. Okay, so first I'm going to tell you what linear means, and then I'm going to tell you what locally linear means. So we don't have an intrinsic notion of linearity in a tangent category. If you have a category, you cannot say what something is linear. Luckily, in a tangent category, we can do that. So, if you think about the algebraic linear algebra, linearity means the linearity of a function. It means that it behaves well with respect to the sum, the zero, and the scalar action. Here we don't have any of that. Instead, we're using more geometric intuition of linearity. We say that a function, you can say that a function f is linear, and f of x is equal to its first derivative, which is equal to f prime at 0 times x. That's kind of the idea that we want to use for linearity. So in a tangent category, I know I haven't told you what a tangent category is, and I'm already telling you something in a tangent category, but bear with me. In a tangent category, a linear object, we're going to call it here later a differential object. Essentially, the idea is that the linear objects should be things that looks like Rn, like Euclidean spaces. So to have a Euclidean space, we're going to ask for the following thing. One, we're going to have an object and a commutative monad on the object. Okay, so we're going to have a 0 that goes from the terminal object into A. We're going to have a plus that goes from A times A into A. Now, forget completely about the structure over here for now. Okay, we're just looking at just an object, and we're going to say that object, when that object is linear. So if you think about this in the Cartesian plane, we have a 0. We have two ways to sum points, essentially. A point here and a point here. I can sum them together. Okay. Second, we're going to say the following thing. If you think about again of R2, for example, and you take a point, if you look at the tangent space at that point, tangent space is canonically isomorphic to the whole space. So if I take Tx R2, this will be the tangent space at x of R2 is isomorphic to R2. If you do that for every point, it means that TR2 is isomorphic to R2 times R2, which in your question, that's exactly what happens in a CDC, in a Cartesian differential category. So the second axiom we're going to ask here is that the tangent bundle of A should be isomorphic to A times A for an object to be linear. Moreover, we also want to say that, so here we have a commutative monad structure. Products of commutative monads is still a commutative monad. If you apply, well, this product will be preserved by T, which means that T of this is still a commutative monad. So you want to say that this isomorphism is going to be an iso of commutative monads. Okay. Okay, so this, I find this amazing because this means that if you have a tangent category, you can say when an object is a Euclidean space. Now notice that fundamentally that this definition depends on the tangent bundle functor. If you change the tangent bundle functor, you will have a different family of objects that will be the linear spaces there. So linearity here is a very contextual notion. Okay, now we're going to add the locally part in locally linear. So we don't want to say that every object is linear, because otherwise this will be a bit too trivial geometrically. We want to say that every object is locally linear. So if you remember here, when I said here that an additive bundle is the same as a commutative monad in the slice. Taking the slice somehow allows us to see the fibers inside of our bundle. Okay, in some sense, taking the slice gives local access to the information of our space. So the idea is that what we want to say. So we want to say that the tangent bundle. So I didn't say what the tangent bundle is actually. The tangent bundle will be the triple formed by the PM, CZ, and S, which we know already there is an additive bundle, we want to say that P of M is a linear object. Not M, not T of M, but P of M, the map. So the problem here, we run into a problem because you have to say that this is an object, but an object where, right? Like this is a morphism, it's not an object. Well, the trick is to say this is an object in the slice category. So it's a linear object in X over M. Remember that the objects of the slice are exactly morphisms that has a target M. So what we want to say is that P of M should be a linear object in X of M. What's the problem here? We have a T in here. So the problem is that for now, we know what linear object means in a tangent category. We need to understand what tangent structure we have here to be able to say that it's P of M is linear in here. So, the naive approach would be, so maybe I can talk about this a little bit. Is that right now? Better?
I can see that.
Okay, great. Can I now go there? No. Yeah.
You can always just monitor yourself on that screen to see how it's going.
I see it.
I just want to ask about this definition. So the T of A, that always comes equipped with a commutative monoid. It always has, right?
So the first part is already done, you're right. Because the first part is already done because we already have an additive structure.
Yeah.
So by dilemma, we already have a commutative monoid structure. So the first part in here is done for P.
No, but
we should understand what the second is, right?
No, so I mean, it seems like we can just have that second point definition, and then because we're requiring this isomorphism.
Yeah. Essentially, what we want to say is that whatever T is in that context of P should be equal to P times in the slice. That's what we want to say.
No, sorry, I'm not talking about the finding T for the slice. I just mean this definition. It seems like we can get rid of the first point. We just require an isomorphism from TA to the.
No, it's an isomorphism of commutative monoids.
No, we have to be careful.
Oh, it's not a.
No, I think I understand that. I understand. Sorry, we have to be a little careful because TA is not a commutative monoid. TA is an additive bundle. So we have to be a little careful because having this is not enough. Look, like, how can I say? Like, if you think about like Rn, right? Like, let's think about a sphere.
No, but in the slice category, he's right that it's going to be a
In the slice,
commutative, right?
But this doesn't live in the slice, right? Not directly at least. So the fun is that
What do you mean by saying it's an isomorphism of commutative monoids then? Don't you mean an isomorphism
from two ways actually? There has to be two ways to be an isomorphism in the commutative monoids. You have to consider both the additive structures, as you said, but you have to also compare with this monoid structure.
But if you just always take that monoid structure to be the one induced by the isomorphism, can you not?
So the point is that this doesn't induce a commutative monomorphism, a commutative monoid on A. It induces to A times A, but not on this. Also, it doesn't gives you a commutative monoid. It gives you a commutative monoid. I'm thinking about this actually. I'm thinking about this.
I mean, so you
We can talk about that a bit later.
back into the slice category that gives a commutative monoid.
There's a way.
From A cross A down to A.
We can talk about that later. But thank you for your question. Yeah. Any other questions? Okay. So maybe I can go here actually. So somehow we would like to have this equation here, but we have to understand what this T is because we have to say in the slice. So the trivial thing you can try to do is to just say, well, T in the slice is going to be T in the base category. So let's try to do this. So if I do Q, this is going to be an object from E to M. This is going to be sent into TQ that goes from T to TM. And the problem is that I run immediately to a problem because I'm not over M anymore, or I'm over T of M. So this is not an object in here. So we cannot redo that.
Post-compose.
Sorry?
I can post-compose with the projection.
I can compose with the projection. That's actually a tangent structure over there. You're right. But we need a smarter one. We cannot do that. So do we have any other idea on how can we do that? Sorry, why did I say that? Why is it so funny? I don't understand. Anyway.
We'll explain later.
Okay, so does anyone have any other idea? So how can I essentially somehow change this one here? I want to slightly change this one here so that I go back to not T of M, but M. Any suggestion?
Can you go from T, like T squared to T?
Not yet. Let's leave T squared for a second there. Something not obvious, but a bit simpler than that. Okay, so the idea is that we can use the 0 here, right? If I use the 0, I can do this. And these two don't compose. But what can I do here? I can take the pullback. I can take the pullback of this along 0. So if I do this, I'm going to define a new morphism. It goes like this. I'm going to call this one here TMQ. So the tangent bundle here sends Q to TMQ. This is sometimes called the vertical bundle in differential geometry. So now that we have this tangent structure, we can do the following thing. We're gonna ask essentially. So when I say that P of M is linear, so the first axiom is already given because we have an identity bundle over there. What about the second component? So we essentially want to impose that Tm of Pm should be isomorphic to Pm times in the slice of P of M. So what is the problem in the slice? Problem in this slice is a pullback in the base category. So this one here is again T2M. That's the equation that we're going to impose. We're going to say that Tm of PQ should be equal to T2M. So be isomorphic to T2M. So this tells us essentially the interpretation of this is to say that the fibers, remember that when we go to the slice, it's the same as looking things in the fiber. The fibers are linear spaces. Which means in particular that T of TXM should be isomorphic to TXM times TXM. This isomorphism here is exactly fiber-wise is captured globally by this isomorphism here. Okay. So this is what local linearity looks like. Now we have to somehow unpack this definition here. So the way in which we do it in tangent calculus is the following way. So we're gonna add a new map with definition. That map is going to be the vertical lift. Vertical lift is a map that goes from T of M into T of T of M. Okay. With this map, we're going to build a new map. We're going to call this one here C, that goes from T2M to TTM. How can we do that? So I'm going to give the details, but it's not very important that you remember the definition here. The idea is that we're going to use L of M times over Z of ZT. So now that we are right here, we can take T of SM, and this gives you TTM. It doesn't really matter that you remember this formula, but the idea is that we're going to take this map here, and using this to build this new map that goes from T2M to TTM. And we're going to impose the following conditions. So local linearity.
So why are we doing that? Why do we want to go from T2M to TTM?
1 second. So local linearity reads as follows. So we're going to say that T of PM. So I want to say that the tangent bundle in the slice applied to PM should be of this form, right? So the slice, to compute this one here, by definition, I have to take T of the projection and pull it back along 0. So I'm going to do this. So here we'll have the V, so this will be V of PM, and this will be TM PM, right? What I want to say is that this one here has to be equal to T2M. So how can you do that? I'm going to use this map over here. I'm going to replace this, and I'm going to say, I'm going to put here T2M, say pi1 PM. Pi1 is going to be first you do pi1 and then you do P. And here we use this special map C. The idea is that we're gonna use an L to build a map C that goes from T2M to TTM, and we're gonna impose this diagram to be a pullback. This is exact to say that we have an isomorphism like this. Okay? Somehow the L specifies that isomorphism. We're choosing that isomorphism. Okay? So this is like the hardest axiom in a tangent-countability, and it's a bit hard because it involves something that is not just algebraic, a little bit more dramatic.
So can I ask that?
Canonical one, yeah.
Could we have required that there is an isomorphism, and then made a requirement that it satisfies some commutative diagrams, and then extract the L from that?
You still need to specify. I mean, you can specify the from here to construct the L.
Yeah,
I think you can do that. Yeah.
Okay.
But the way in which the axioms are written is we prefer to start with the L and then conclude that we have an isomorphism here. Okay. Yeah, because essentially we are saying that if this is a pullback, this is exactly the pullback of this by itself is going to be exactly TM. So this is going to be TMP PM, right? So to say that this is the same pullback, it means that this has to be isomorphic. So from there, you can reconstruct the L somehow. Yeah. So from here, you can construct the C, and then you can do some tricks to reobtain the L, essentially. So that's another way to do that, yeah. Okay, so I'm tired. The final axiom the final structure that I'm gonna require, and I promise that it's done, is the canonical flip. So what is the canonical flip? So maybe I should tell you a little bit of differential geometry. In differential geometry, there are different ways to define a tangent vector. One way of thinking of tangent vector is as a point, and you're thinking, so here's going to be your M. One way of thinking is a bit more geometric, is to say, we're going to take all the possible paths that starts at the point X, one, two, three. You take all of them, and you're taking an equivalence class of those paths where theta is equivalent to phi to gamma is equivalent to theta if and only if gamma 0 is equal to x, which is equal to theta 0, and the first derivative will be this vector here, is equal to the first derivative of gamma of theta and 0. So essentially, you're saying that you're taking all the possible paths, and at least at the beginning, they point to the same direction. Maybe after a little bit, they can do something else, but right at the beginning is the same. So this way of thinking is to say that tangent vectors are infinitesimal paths, because it only matters what they do very close to the point. Another picture in mind in differential geometry is to think of tangent vectors as differential operator. The differential operator is something that goes from D, it goes from C infinity M into R. C infinity M is going to be the algebra of smooth maps from M to R. And it satisfies the following conditions, so it's going to be R linear. We have to be a little careful here. So R is actually say that R is actually going to be, so if you fix the X, right? We have a map that goes from sorry, 1 second. Yes, we get a map that goes from C infinity M into R, right? Actually, I don't have to say that. I can start. Let's forget about the algebra. Just like give it the form one. So we have this, and moreover, they satisfy the Leibniz condition. So P of F times G equals to F of X, P of G plus G of X, P of F. Okay. Turns out that this geometric picture, is equivalent to this kind of picture in differential geometry. But the main idea is that if this is true, then we can think of tangent vectors as directional derivatives. They will correspond to directional derivatives. Derivations, actually. So if you have that, one thing we want to say is that if you take the directional derivative of F along U, then you do this along V, it's going to be equal. One of the fundamental results of calculus is that this is equal to taking the same things, but the other way around. So you take first P, then you do U. So we want to have somehow a way to switch between those partial derivatives, those directional derivatives. The canonical field does exactly that. So the idea is that we have an isomorphism C that goes from TTM to TTM. I haven't said that, but the vertical leak is also natural, and so is the canonical fit. And this is going to be an isomorphism, and it satisfies some properties. And the idea is that this here, C of M, does exactly this flipping. So let's try to understand this a little better. So we have kind of like a hierarchy, right? M contains points. T of M contains, the points of T of M are the vectors of M. So we have a point and a vector. TTM is going to be a vector in T of M, which is a vector of vectors in T of M, in M. Which means that we can think of this as like an infinitesimal homotopy in some sense. So you have this, you have like an infinitesimal tile somehow that is oriented like this. Okay. The idea is that the linearity condition here, local linearity condition, tells you that this filling here is just to give exactly a tangent vector in here. So T of M can be understood as X, U. This will be a point in here, so a tangent vector in here, right? Comma, something else, V, W. V is going to be a tangent vector because it's going to be a variation of X. But what is going to be your W? It's going to be this filling here. The linearity here tells you that W is, again, just a tangent vector. Okay? So this is a tangent vector. So in this picture, having said that before, L takes an X and a U, and it sends to X, 0, 0, U. So it sends this vector here to this vector here. And C takes X, U, V, W, and it sends from here to X, V, U, W. Okay, so it flips around, it flips these internal ones here. And it turns out the naturality of this corresponds exactly to this equation here. Okay.
Can you maybe, sorry, show on the picture, please, the L?
The C. The L is not obvious, but the idea is that you are sending essentially, you're sending a vector, right? something that looks like this. So you have this vector v. I'm gonna draw it, but you can think of this as the infinitesimal homotopy from v to itself.
So I'm a bit confused because in one case we have x0, in the other case we have 0u.
Sorry, it's gonna be u. Sorry.
So I'm wondering
X
what
and u. Right. This is gonna go into x, u, and essentially the idea is that you can think of this as u like this. It's gonna be the trivial path that corresponds to the 0 to the
So I
0.
don't see the two u's there. That's why I'm confused. So there's only one u there. There is L of xu is equal to something that only has one u in it, and there are a bunch of zeros.
You're right. 1 second.
I think the first u is going to become 0.
You might be right. You're right. I think it's gonna go. Oh, I see. I think it's gonna be. Yeah, you're right. It's gonna goes like this. Sorry, you're right. It's gonna goes like this, and the other u is essentially encoding in the filling. It's a bit hard to understand for me what the picture will be in that case for the L. It's a bit clear for me what the
other
does.
I think the other u goes from 0 because the tip of that dashed line is 0, right? No. Wait, sorry, never mind.
I might be confused about this. Sorry.
Yeah, okay.
The picture here is a bit hard to understand that. But the C is a little bit more understandable. The C does this. This is a picture, of course, but the idea is that it flips, send this one here to this one here. Flips these two. This. Okay. Any questions about this? So let me try to briefly recap.
Wait, so is there? Well, I guess I don't know what's the condition on the CM.
So I haven't told you the axiom.
Oh, okay.
But for now we have this like isomorphism.
Okay, just summarize.
Actually spell out the whole definition. Maybe trying to skip some details because it's a bit long. But the idea is that the following is the definition. So the definition: a tangent structure the following data. We have tangent bundle structure. We have a projection of 0. We have a sum. We have a lift. A canonical flip. Sometimes we also ask for negatives. If we have that, we say that these are tangent category of negatives. So the first axiom is that P Z S is an additive bundle. And moreover, Tn preserves the n-fold of x P's of Pm. Okay. Secondly, we're going to say that, so I haven't told you this, but if you take P here, you take Pt of m, you take 0 here, you take the lift. So these two pairs form an additive bandomorphism. Additive bandomorphism. So what does it mean? It means that it preserves the projection, the 0, and the sum. Okay. And we're going to have that the canonical flip does the same thing. So TTM, TM, we have TP, here we have PT. Here we're going to put C, just an additive bandomorphism. Okay. So here we're essentially saying that both the lift and the canonical flip are compatible with the sum and the 0. Okay. what else? Now we're going to have some properties of L and C. So we're going to say that C do C twice. So T, C, do C twice. Going to be identity. You think of this like if you flip the do twice, it's the same as doing this. So maybe I can draw this one here a little bit pictorially. We do this, the same doing this. Now, if you think about C as like something that does this, then you can do the following thing. You can flip this one here. We have T, T, another T. You can flip the first two, then you can flip the second two, then you can flip this one here. This is just a way to say it. You have to see, this will be essentially, this block here will be CET. This block here will be TEC. This block here is CET. We're going to say that this is the same as doing nothing here, flip this one here, flip this one here, flip this one here. If you follow this one here, you're keeping the middle one fixed. And you imagine to move this string to the other side. Okay. We're going to do this. We're going to require, there's so many things. So T, you can do L, goes in TT. You want to do T of L, T, T, T. You can also do L again, and you're going to do L of T. It'll be the same. So L is co-associative. Then we have some compatibility between L and C. Other compatibilities. I'm not going to write that. Other compatibilities. And most importantly, we have the local linearity condition. So that diagram is a pullback plus local linearity. I know that this looks a lot of axioms and structure, but if you ever study differential geometry, it's nothing.
Looks like we have some sort of symmetric braiding going on there, right?
Sorry?
Looks like we have some sort of symmetric braiding. C.
Yes, C is going to be a symmetric braiding, exactly.
Okay, and then L almost looks like some kind of co-product. Sorry, co-multiplication. Or is that?
Yeah, so L behaves like a co-multiplication, but it's not co-unital.
Oh, okay.
So it's very important that L is not co-unital. In particular, you have the following property. So remember that I showed you this, right? L composed with P is equal to PZ, but L itself is not co-unital. So if you are interested in like this kind of structure, the tangent model factor is a monad using the additive structure. So the additive structure gives you a monad. It doesn't give you a co-monad though. It's like something is less than a co-monad because L is not co-unital. Any other questions?
What about the leaf brackets on the section? You haven't spoken about that, right?
I'm going to arrive there. I have to introduce vector. So I'm not sure how much time do we have today for doing that. I would like to go on examples though.
You have 12 minutes left.
12 minutes. No, enough. Okay.
But is that part of the axioms or is it part of?
No,
It's not part of the axioms.
It's a result.
It's the results.
It's a result. You can do that when using this structure here. And very important, you need to use the universality of the lift. Like the leaf bracket use essentially every structure that we have there.
Oh, that's quite nice because the usual differential geometry proof is a little bit ugly. It depends which way you do it. If you do it by functions, it's easy, but if you do it by tangent vectors, it's kind of hard.
If you do, yeah, like I've seen that like using functions, which is I guess easier. Okay, so if you do that, yeah.
I'm just wondering again about this definition of linear objects. So I agree that superficially it seems like it depends on the choice of T, but I'm guessing there's also examples where you show that it does actually depend on the choice of T.
So the point is that some T's will give you the correct, the what you expect to be the linear thing. Other T's won't. In the correct context, it will give you what you want. But if you take another T, it might mean something else. Let's talk about this actually. So I'm going to try to be a little fast on a couple of things. I will never finish, it's too much. So examples. So as I said, geometry is contextual. And The next example will show you this dramatically. Every category is a tangent category. So, trivial example. Every category, X, has, if you take the identity functor, X, and take P0, sum, lift, and canonical flip, and also the negatives to be just identities on the identities.
What about the linear structure, by the way? How are you going to get the linear structure?
We'll just have, the linear structure will be just trivial because this will be automatically a pullback because everything is going to be just identity. So the idea here is that something very important, like tangent categories are a context for differential geometry. If you change the context, you have a different type of differential geometry in some sense. So every category is a tangent category. This is the geometric theory that tells you that there's only one possible direction, trivial direction. It's the thing that tells you stay there forever. You have no directions. It's the trivial one, but it's still important. If you want to have a more topological understanding of this kinds of theory tells you that your points are absolutely discrete. Every point is isolated. There's no way to connect any other point. You can only stay at that point. So this, of course, is not the only example. Otherwise, we would have finished here. Otherwise, we would have killed me after this an hour and a half of doing that. So we have also another important example, which is a categorical example, which is MAN. MAN stays for smooth manifolds. And very importantly, the category of smooth manifolds is a tangent category. This essentially captures differential geometry, the example of differential geometry.
Which kind of manifolds are we considering here?
Both. I mean, whatever you want, I guess. Okay. So there are different flavors of smooth manifolds. You can look at paracompact, Hausdorff, blah, blah, blah. Or you can only just look at the one that are not necessarily things in Rn. So both of them give tangent structures.
How well does it fit the theory of infinite dimensional?
There's also a way to do a thing I call convenient manifolds. This is also a tangent category. Also, infinity ring is a tangent category. Infinity ring opposite is a tangent category. So smooth manifolds, the tangible functor will be exactly the tangible functor in differential geometry. I'm not going to tell about the other structure because I don't have enough time, but you can do that. And if you Google Wikipedia, the vertical lift and the canonical flip, you'll find a definition there. Okay. Then I'm going to go something a little bit more interesting. So let's take a category, not interesting, a bit different, I guess. So now we're going to go a little bit more algebraic. So imagine you have a category X. In the category, we have biproducts. So biproducts means that you have finite products, finite coproducts, and they are canonically isomorphic to each other. In particular, you can think of these as vector spaces over a field, or you can think of these as mod R over unital and commutative ring R. So the idea is that T of M is defined as M plus M. Projection goes from M plus M to M, and just forgets about the second component. So here I'm saying that here I'm going to have points, here I'm going to have vectors. This is a very simple one. It's more similar to like a CDC. It's actually simpler than a CDC. So here is essentially going to have P1, P1. The 0 is a byproduct, so we can also include the first component. So this one sends X and U, X. This sends to X into X0. The sum, the pullback of P along itself gives you 3 copies of M. This takes X, U, and V. And it takes X, U plus V. Now, what is the plus here? If you have byproducts, you always have a plus of functions. You have a way to sum the two things together. You can think of this as the map that sends identity into identity in the same thing. The lift is going to go from M plus M, M plus M plus M plus M, takes X and U, X, 0, 0, U. And the canonical flip, you guessed it, it's going to flip the internal ones. So X, U, V, W, X, V, U, W. this gives you tangent structure. It's somehow a bit stupid because you're trivializing everything. There's not too much geometry here. But it's a very important construction because from this very simple one, we can build new ones that are more interesting. Okay, so maybe I'll give you, is it?
5 minutes.
5 minutes? Yeah. Okay. So I can tell you, I can give you the last final example, and maybe we can talk about algebraic geometry next time, maybe. Okay, so the category C alg R. So this is going to be commutative and unital R algebras. So the idea goes as follows. So I'm going to consider the following ring, the following algebra. I'm going to call this one here R epsilon. So R epsilon is given by you're taking polynomials in R and you're quotienting by x squared. So think about polynomial. You take a polynomial will be a plus bx plus c x squared and so on. And every time you have x squared, this gives you 0. The only term that really that remains is a plus bx. We're going to write it here as a plus b epsilon, where epsilon squared is going to be equal to 0. The idea here is that these, you can think of these as like the points. It will be like an infinitesimal thickening of the point. So the idea is that this object here has some structure. So we have a P that goes from R epsilon into R, and you send just epsilon to 0. 0 sends for R to just R. Now we have to understand the sum. So the pullback of P along itself is given by this thing. It will be R. You take two variables. You're quotienting by x squared, y squared, but also x and y. Okay. And you send this one here into R epsilon. This is the one that sends, so this now here I have a plus b epsilon 1 plus c epsilon 2. It sends it here into a plus b plus c epsilon. Lift goes from R epsilon into R epsilon of epsilon, but this is the same as taking R epsilon if you want. So this sends a plus bx into a plus b epsilon tensor epsilon. Finally, the canonical flip goes from this, oh gosh, I'm not do that anymore, into R epsilon. The idea is that here we have a plus b epsilon tensor 1 plus c 1 tensor epsilon plus d epsilon tensor epsilon. And this is sent to a plus c epsilon tensor 1 plus b 1 tensor epsilon plus d epsilon tensor epsilon. Now notice that this is very similar to this one here, but it's not as trivial as the other one, because now globally we cannot really separate them anymore. Okay, so maybe we should stop here. But yeah, so the next example I would like to tell you a little bit about, maybe next time, will be the category of fine schemes, which is probably one of the most interesting ones that we have now. Thank you. Okay, so last time we essentially defined what a tangent category is, and I just like put here the short version of that. So a tangent structure on a category X consists of this concept structure. So we have an end effector that we call T, we call the tangent end effector, a projection, a zero, a sum, a lift, and a canonical flip. These three gives us an additive structure. The lift gives us a local linearity condition, and the C essentially is a symmetry that encodes the symmetry of direction derivatives. That was kind of the idea of last time. Of course, those things satisfy some axioms. So the first thing I wanted to do today is to give you an interesting example of a tangent category that is being recently studied quite a lot. Like people are working quite intensely on this idea. The main idea of this example is to try to study some aspects of algebraic geometry using tangent categories. So my ex-supervisor, Jeff Cockrell, wrote some really nice notes that you can find in this link here that you can click later on the whiteboard. So that's how it works, right? You write it down and just click it, right? That's how it works. So what I'm gonna say are essentially is a short version of these notes. They're very beautiful. So if you're interested in any of that, you do a really good job in like really explaining things in a very clear way. Okay, so I'm also gonna say that I'm in any possible way, I'm not an algebraic geometer. I'm not sure if I don't want to be, but definitely I'm not one of them. So I tried to study a bit of algebraic geometry, and again, as in the same way as when I studied differential geometry, I immediately noticed that it's quite cumbersome. The basic definitions. Algebraic geometry is also not very, is not known to be easy, at least not in my understanding. So if you go in the usual way of algebraic geometry, my understanding, they define notional schemes, and then they talk about fine schemes, and they look at this category and blah blah blah. So it turns out that one of the main results that you have at the beginning of when you study algebraic geometry is that the category of fine schemes that I'm just going to write up is equivalent to the category of C ring opposite. And more generally, if you're looking at affine schemes over ring R, you can forget about what I'm going to say now, but just I'm going to say that for completeness, is equivalent to the category of commutative and unital algebras over R opposite, where R is going to be a commutative unital ring, is fixed. And if you're looking at this category here of commutative and unital R algebras, you look at the opposite category, it's going to be equivalent to that. So the first approach that we're going to have is to forget completely about this part here. We're going to look directly at this category here. So the idea is that we would like to do the following thing. We would like to make this category here into a tangent category. And we're looking at these as the actual affine schemes. Now, I just want to say this because if you're an algebraic geometer, you would like to maybe work on this category here. But for the purposes that we're going to talk about, we're working directly on this category here. Okay? But of course, the equivalence transposes a tangent structure.
Okay, that's fine. But I'm just getting back to the definition. I forgot a little bit from last week, but there was the Lie bracket of vector fields. Where is that captured in the?
So we haven't talked about vector fields yet.
Yeah.
I'm going to give you this example, and then we're going to talk about vector fields.
Okay.
Vector fields are not a concept for now. So, okay, so here I'm going to give you the definition of what is the tangent structure on affine schemes on this C alg R opposite, and then we're going to try to understand a little bit that example because I think it's very interesting. So first of all, I have to tell you what the tangent bundle functor is. So remember that we are in the opposite category. So I'm going to write everything as it was a morphism in C alg R. But remember that we're in the opposite category, so everything goes in the opposite direction here. So tangent bundle functor, T of A. So we're going to take A as C alg R, commutative unital R algebra. T of A is defined to be the symmetric A algebra of the module or Carr differential of A. This is not exactly an easy definition, so I'm gonna try to unpack this definition. So this is called this is an A module, and it's called the A module of Carr differential. Carr differentials. Differentials of A. And symmetric A algebra, it's gonna be maybe gonna say that in a second. The symmetric A algebra of blank. Okay, so what is the modulo of Carr differential? Does anyone know what is the modulo of Carr differential is here? Do you have any idea what it would be?
Yeah.
So the idea goes as follows. So we have to define what a derivation is, first of all. So if you have an A algebra and an A module M, a derivation is a map like this that is R linear. Very, very crucial is not A linear, it's R linear. and which means that this means that that a delta of RA plus SB equals to R delta A plus S delta B. And moreover, it satisfies the Leibniz rule, which is the product rule. So delta A dot B equals to A dot delta B plus B dot delta A. Now notice that because M is an A module, there's an action of A over M. So this is an element in M. This makes sense. This makes sense, and I'm going to sum them together. That's what a derivation is of an A algebra over an A module. So the idea is that the Cayley differential is a very special module that has a very special derivation. So the module Cayley differential can be understood as the A module generated by the symbols dA for each A in A. This is just a symbol for now, such that DRA plus SB equals RDA plus SDB. So D somehow is actually R linear. That's what we were saying. R and I haven't said that, but R and S are in A, and R and A and B are in A. Okay, and moreover, D of AB equals ADB plus BDA. So I'm freely generating a module, an A module, generated by those symbols, and such that those symbols need to satisfy this relation. A more concrete description of this module is as one way of describing this is the kernel of the map, the multiplication map. So A tensor A into A is going to be the product map. You take the kernel, that would be this A module. This is another way of thinking of this. So this looks a little bit abstract. So let's try to go a little closer. Let's try to understand what this does. So the idea is that the Cayley differential represents every derivation. So notice that D satisfies the exact same conditions as a derivation. So the idea is that for any derivation A, there exists exactly one A module map. So now this map is A linear, such that if you take A into delta A, this will be D, that sends A into D of A. Okay? And here you're saying doing this will be your delta. This is exactly your map R. So if you look at this a little bit more categorically, this means that if you define this space of derivations from A to M, where M is an A module, okay, this is isomorphic to the home set in mod over A between omega A and M. So this idea here is this concept goes as follows. The modular differential is a way to pass from derivations to A modules morphism, so A linear maps. Okay, if I have a linear map between the Cayley differential and M, I get a unique derivation. If I have a derivation, I get a unique map. So in some ways, it says that the modular differential is the object that represents the functor there A M. M is going to be blank. A there of A blank. Does it make sense what I'm saying here?
Yeah.
I know this is kind of a hard thing, but the idea is that
Why are you not explicitly saying that omega A is the free derivation?
It's a universal derivation, yeah. Not sure if it's kind of like a free derivation, yeah. You can think of this in this way, yeah. So the idea is that this modular differential is a way to capture all the derivations of A in a unique object in A module. Okay, now the idea is that you do the differential geometry, you know that tangent vectors are related to derivations. I talked a little bit about that last time. So here we are somehow, if we want to do algebraic geometry, we somehow have to capture the derivations of the algebra A. The problem is that here, if I assign to A an A module, I'm going outside of the category of C algebra R opposite. I'm going to A module category. So instead of doing that, we have to replace this A module back into the original category. To do that, we're going to use this functor here. So the idea goes as follows. I'm giving right now a very abstract definition, but it will be a little clear when we'll see some examples. Maybe I do here. So I have the following functor that goes from, it goes like this, or maybe, what am I doing here? I've never used this notation here before. So if you take C alg R, so let's look at the co-slice category. Second. Alg R. So the co-slice category has per objects morphisms of this type from A to B. So the target is always A. The idea is that there is a way, there's a canonical way to equip B with an A module structure. So let me call this one here maybe MB. Now MB as a set is just going to be B, and the action of A is going to be A times B into B into M of B into M of B. It takes an A, it takes a B. If this is called F, it's going to go into F of A times B. So B has a multiplication, so I can use this map to induce an A module structure on B. Okay. The idea is that this functor here has a left adjoint. This is exactly sim of A. Okay. So now the idea is that we have here our modular curve differential. If you send this one here into sim of A into something here, you get something of the following type. You get something A into sim of A modular curve differential. Okay. Does it make sense what I'm saying for now? This is a very abstract definition. We're going to the examples slowly. Yeah.
Wait, could you just remind again, what is the C alg R?
So C alg R is the category of commutative and unitar R algebras. Maybe I'll say here. C alg R commutative unitar R algebras, and of course going to be R algebra morphisms, homomorphisms of R algebras. Okay, so we have this abstract definition. So again, I said again, the tangent model functor sends an algebra into the symmetric algebra of the modular curve differentials. The symmetric algebra is not really super important. Like it is important, but it's not. It's a way to just simply like take an A module into an algebra, back into an algebra. But the interesting piece is really the modular curve differentials, because these capture derivations. So before I go further, let's try to understand this functor a little bit more concretely. So if I give you a presentation of an algebra, you should be happy. You should be happy. You should know that there will be an algebra that has that generator and presentations. So T of A is generated by all A's in A's and all symbol DA for each A in A, satisfying the following conditions. If I multiply an A and a B in T of A, it's exactly the same as multiplying A and B in A. Does it make sense, this notation here? So essentially, this means that in T of A, we're going to have a precise copy of A inside. Okay. Remember that this functor here sends an A module into something that goes from A into this. So we have this map here. So this is the map that sends A into its copy inside of T of A. Okay.
Sorry, what is your heading there? Generated by all A in A, comma, all
symbols D of A for each A in A.
Okay.
Such that on the A's, on the elements of A,
yeah,
the multiplication acts exactly as in A.
Good.
And then we have exactly the same relations as these. So we have D is R linear. And D satisfies the Leibniz condition. This is how it's generated. And let's now do an example, more concrete example. So e.g.
How can I multiply to DAs with each other? Can you do?
Or just freely, like.
So you take the free R algebra generated by A and D of A. You do have a multiplication there.
I see.
And now you impose these relations.
I see.
Okay. So let's take A to be R of X. R of X, yeah. Okay. So now we have to compute T of R of X. So let me see this.
Wait, sorry, was B also from A in that first?
B, A, and B are in A. Yeah. For each A and B in A.
I don't know if this is at all helpful, but I also think this construction is the left adjoint to tensoring with the ring like R epsilon, where epsilon squared.
Yes. That's exactly a very important thing. So as you said, T of A is the left adjoint. So T is in theology is going to be left adjoint to tensoring by R epsilon. Maybe I can comment a bit about this later.
But it's also nice to think of it from a function of points perspective. So it's like you want to think, what does it mean to give a map into that thing?
So that's a good question.
The adjoint little thing is in the wrong direction, but you said left adjoint, but
I always write it. Left for me is when it's on the left, right. And right is when it's on the right. Okay, so if you want to define the whole thing as a functor, you're right. I have an f that goes from A to B. I have to tell what is T of f. So T of f goes from TA to TB. And now we have a description of what TA is. So as generators, this sends A into f of A, and D of A sends into D of f of A. Okay. So if I tell you what the generators are, believe me, this satisfies the relations, so it leads to the quotient. Okay, so now we have a factor. Now let me try to explain what this is. Let me see if I remember well how to do that, because I'm not doing super well. Okay, so we have the following thing. So this is generated by all the polynomial and all the D of a polynomial. We have to understand what this D of P is. Okay, D of a polynomial is. So let's write the polynomial as a sum for k goes from 1 to n of ak x to the power of k.
0
to 0 to 1, yeah, right. Yeah. So if you take d of this, so d of the sum is a finite sum, and d is R linear. So I end up with something like this. I can move the d inside essentially, right? So I get the sum k that goes from 0 to n, and I get ak d of xk. Now, because of the Leibniz rule, this gives me exactly k x to the power of k minus 1 dx.
Except on k0. Sorry, I gave you trouble by introducing.
That's right. So let me try to be a little more precise. If you want to be very, very precise, if you want to be a little pedantic, you say, let's take the zero part. So this will be ak d1. Oh yeah, maybe I actually should say that. If you're not in characteristic 2, maybe it's not obvious.
You need it.
D of 1 is equal to 0. You have to impose that if you're not in characteristic 2. So d of 1 equals 0. So this goes away. Now we have a sum from k that goes from 1 to n, right? And then we have ak x to the power of k, k x to the power of k minus 1 of the x. Okay, and if you want to shift a little bit, so this goes away. So this goes from k from 0 to n minus 1 of a k plus 1 x k. And what is important of this formula? Here I'm just using essentially our linearity and the Leibniz rule. What is important of this formula? The fact that this symbol here is fully generated by x's, a's, and d of x. Which means that the only thing that is really remaining here that is new is just d of x. So it turns out that from this reasoning here, we have the t of r of x is given by r x. Okay, does it make sense what I'm saying? So let me switch it again. So this is generated by d, a polynomial, and d of a polynomial. But we've showed that d of a polynomial is just another polynomial multiplied by dx, which means that this is just going to be rx. It's going to be, let me try to be a little bit more precise. It will be rx tensor rx dx. But this is the same as taking rx dx. So I'm taking polynomials in two variables. That's it.
What is Rx close bracket dx?
You think of these as two variables.
No, the one on the left, the last one on the.
Oh, just like you think of this as multiplying every polynomial to the x.
And is that it's not really a strict equality, is it? Okay, nice.
I don't know. It's gonna be isomorphisms.
And this is our linear case, right? So this is like R2.
Exactly.
R, I guess.
So what I'm saying is that R, you can think of the R of x as just a line because we have one generator. So T of R is going to be the whole plane because we have two variables. Okay. So on simple things, this is behaving well because we know that the tangent functor duplicates the variables. So you would expect that T of R will give you exactly something that is two-dimensional. Okay. Now let's start to add some more interesting things.
Do it for the circle.
Yeah.
Okay.
I'm going to do a circle. So another example, of course, is I'm not going to do that, but believe me, if you actually take any finally generated R algebra, so now I'm taking polynomials in n variables. If I do the T of A, I'm just duplicating the variables. Okay. So this is going to be R of x1, xn, dx1, dxn. Okay. So let's now do something a little bit more interesting. Let's do the circle. So let's take. So I have to say a few things here. So let's now take this algebra here. A equals R of x and y. We're quotienting by the following the ideal generated by this polynomial. So let's take now R to be real numbers, just for simplicity. Yeah. So clearly here I have the equation of a circle. So the first thing you need to understand is, why do you think that this is a circle? Like, what does it even mean to have a circle here? Okay, because this is just a ring, right? So if you're like me, and when I saw this thing, I was like, I'm not sure if this makes any sense. So the question could be, what is a point of a circle? So a point in a category. Does anyone know what a point of a category is?
It's a map from a single element set or singleton into your space.
So a point, maybe see this, a point is or a generalized element, no, a global element, sorry. So a point is a map in a category that goes from the terminal object into your object M. So why is that? If you think about this in set, terminal object will be the singleton. So having a map from the singleton into M, it spits out exactly, it gives you a choice of one point. So what are the points in C algebra? So points in C algebra.
Good.
Let's start with C algebra first.
Not all.
Let me just do C algebra first.
Yeah.
So the terminal object here, the terminal object is just 0. So how many maps I have from 0 to any algebra A?
0.
No, just only one. So trivial. I only have 1 point. So this tells us that maybe C algebra R is not very geometric place to work with. Yep.
Does this unital not force you to also send 0 to the 1 and then it collapses the?
Yeah. Assuming that 0 and 1 can be equal.
But if they're equal, then isn't the ring trivial?
Yeah, that's exactly what it is.
Yeah, so it's there's no map unless A is.
There's no mapping interesting here. But remember that we're not in C algebra R, we are in C algebra R opposite. Right. So let's see exactly what does it mean to have a map in C algebra R. So a point in C algebra R opposite. So here the terminal. I'm saying the terminal, like, are we okay with terminal? Like, do you know what a terminal is? It's going to be an object that has a unique map from every other object into that. Okay, so it's like a sink, if you want. So the terminal object now is R. And a map goes, well, this is going to be initial in C algebra R, becomes R. Which means that a point corresponds to a map that goes from R into A in C algebra R opposite, which corresponds to something that goes from A into R. In C algebra. And also let's try to understand what the points of a circle is in this sense.
Well, let's start with maybe just R of X. Just start with that.
Sure, let's do R of X. If I do R of X, point will be an R algebra map. This map is fully specified by assigning X to a number. This is fully determined by X into something. So this gives you exactly a point in R. So think of this R to be the real number. It gives you exactly real numbers. Now let's take something a little bit more interesting. Let's take x, y, and let's take the circle. So x squared plus y squared minus 1. Our point here is going to be something like this. Now this map is fully specified by the assignment of the generators. So it will be a value in x. Let me call this one here A. A value for y. Let me call this one here B. So maybe I'm calling this one A and B. However, this has to be an R algebra map, which means that this map needs to be compatible with the products, which means that this forces A and B to satisfy this equation. Because if it doesn't satisfy the equation, this map does not lift to the quotient. So this forces the following conditions: A squared plus B squared minus 1. Really equals 0. Sorry. Equals 0. But this clearly is a point of the circle. So one way of understanding these kinds of things is to say that points of those things are exactly points of the circle. So clearly there is something geometric going on.
That's what I was referring to when I spoke about the functor of points perspective. Yeah.
Yeah. I guess I'm not very knowledgeable on it.
Exactly this.
Yeah.
Yeah, it's just allowing rather than just having the global points, you allow that to vary.
So again, I'm not an expert in algebraic geometry, but I know that one big idea of algebraic geometry is that if I know the points, this doesn't mean that I know the object. Because it's not like there are some objects there cannot be there might be two objects in your category that have the same points, but they're not isomorphic to each other. So this is very important. Maybe I'll comment about that later. But for now we have that, at least for the circle, this works pretty well. Like we clearly have a picture of the circle. So maybe we can draw a picture.
Yeah.
Which would be this. So now we would like to understand what T of these is. Here I'm going to say some abstract nonsense a bit. So as you pointed out, T is a left adjoint, and the quotient is a colimit, which means that T preserves colimits. Therefore, this means that t distributes along the quotient. So what I'm saying is that thanks to this abstract property, we can write this one here as you're duplicating the variable. So you apply t to this, right? So you have dx and dy, because this we already computed what the t of the free is. Now we have, so remember that we always have a copy of the original object in. So we're going to have the same relation for x and y. And now we're going to add a new relation. And the new relation is given by differentiating this relation. So this will be d of this relation. So what would that be? We just use Leibniz again. This gives me r of x, y, dx, dy, quotiented by x squared plus y squared minus 1. Now we can use Leibniz, and this gives me 2x dx plus 2y dy. 1 goes to 0, because d1 is going to be equal to 0. And that's it. Okay? So now we have a very computational understanding of this abstract thing that I told you before. So if you have something that is finally generated, you can duplicate the variables, you take the original relations, and then you have to differentiate those relations. You have to differentiate those polynomials that define that ideal.
So can you explain a bit why it's a bit unclear to me why when t commutes to the covalent, we just differentiate the general.
So this comes from the fact that this comes from a property of left adjoints. So so he mentioned that t.
It's a preserves a co-equalizer, but there's still some work to do to check that that's actually the question.
Sure. But it turns out that that's exactly what happens. So the intuitive idea is that t is a left adjoint, and a left adjoint preserves equalizers. This is co-equalizer. So the quotient can be understood as a co-equalizer, and so t of a co-equalizer is the co-equalizer of the t's. That's what's happening here. So essentially, the two operations commute somehow. And this is because t is a left adjoint. So this is how essentially we compute in the end the t's. Okay, so now do we know what t of the circle is? To understand if this is the correct definition of t of the circle, let's maybe compute a tangent space. So first I have to tell you what a tangent space is in a tangent category. So definition.
So you're not going to tell us first what the points of that thing are.
I think it's better to understand the tangent spaces maybe. So if you want to see the points, but the problem is that like why is it a bit harder to understand? Because it's going to be 4-dimensional. So yeah, it is something, but it's 4-dimensional. So maybe it's a little bit more geometrically hard to understand. But tangent spaces simplify the problem.
Well,
is it
it's embedded in 4-dimensional.
Yeah,
but it's
a
2-dimensional.
Yeah, no, you're right. It's going to be right. It's going to be 2-dimensional.
It's literally going to be
No, it's going to be you're right. It's going to be 2-dimensional.
the usual tangent bundle of a circle.
Yeah. It's the thing like I have to like I cannot draw it in on the plane. I have to draw it in.
But you can, but just drawing a little dot on the circle and a little tangent vector, and then the collection of all those things.
Sure. Let me do tangent spaces. I think it would be
Yeah.
So definition. So a tangent space. So a tangent space and the space of a point A in a tangent category. Can you guess what would that be? How can I define the tangent space? So exactly first of all what tangent space is in general, like as a concept. So the idea is that I have the tangent bundle that contains all the possible tangent vectors at every point. I'm restricting to those vectors that are over a specific point. So how can I do that? Do you have any idea? Any suggestions?
Actually, point in the tangent T of M.
So what I have is definitely T of M.
That'll be a tangent vector.
Let me have this. I have to somehow restrict those things into something a bit smaller that only contains the tangent vectors over that point. So
Pullback.
pullback. So I take A, and I take the pullback of this. I'm going to define the tangent space to be the pullback of P.
So
along A.
Marcello, can you remind the camera that you're there? Thanks.
Okay. So this is called the tangent span, this tangent space. Out. Okay. So with this abstract definition, now let's compute the tangent spaces of the circle. So we have to understand what is, first of all, pullback in C algebra opposite. So a pullback in C algebra opposite is a push out in C algebra. So a push out in C algebra R is the following thing. So I have a diagram like this. I have two maps like this. If I take the push out, this will be exactly given by the tensor product over A. This is a property of, this is like something that is well known in the category of C algebra. So the push out is exactly given by the tensor product, okay, of commutative and unital algebras, R algebras. Okay, so if we know this, maybe we can now understand what this is in the case of the tangent of the circle. So we have, let me call maybe it's called C to be R of x, y in x squared minus squared plus squared minus 1. Okay.
Sorry,
So
I'm confused. I would have thought that it would be the top arrow that's the tangent space. That it should be like a sub.
So to be clear, that will be, yeah, you're right. That will be just the objects. Yeah. The object is the tangent space. Sorry. I've been drawing. I've been selecting the other map for too long.
Well, it's the unique map to one. It's the circle.
Yeah, exactly. No, because this doesn't mean. This
Being morally, it was right.
Yeah.
Yeah, sure. It's like the idea that like tangent space, you can think of this as the bundle over a trivial point. If you want to. Okay, so let's try to compute this one here in this category here. So let me first of all do this one here in C algebra opposite. This corresponds to this. So I have we already established that a point is something that goes like this. So that goes from C into R in C algebra R. Okay, so in C algebra opposite it goes the other way. So we have our point is going to be 1 into, I usually use this one here as a terminal object, sorry for that. So in C, right, AB, and taking the tangent bundle and have to pull back along this. So I forgot to tell you what the tangent bundle is, so maybe that would be a very important part. So remember that, as I said here, on this abstract construction, we have this functor here gives us not just this, but also a map like this. Okay, so this will be exactly the projection. Remember that we are in the opposite category. So in the opposite category, this goes from here to there. So maybe I say this. The projection goes from T of A in C algebra R opposite, which corresponds to something that's from A to T of A. So remember that in the definition, in the description I gave about generators, T of A is generated by A's and DA's. And if I multiply two things in A, it's the same as doing exactly the same in A. Which means that I can send A to just A. That is the projection. Yeah. So if I have this, now I can compute this. This would be T of C. So now we are in C algebra R opposite. We have to dualize it. This corresponds to a push out like this. So I have P of C that goes into T of C. And here I have AB into R. And I'm taking the tensor product between T of C over C and R. Yeah. So this is the tangent space of of C at AB. So what does it mean tensoring by R? So R becomes, so to have a tensor, it means that this is going to be a C module, and this is also going to be a C module. The C module structure here is induced by P, because C goes to T of C, therefore this becomes a C module. Moreover, R is also a C module, because we have this map here. So this means that we are quotienting, we are generating everything by taking something in here, and we are imposing the equation that if I am tensoring this way with something here, the action can move around, right? So from there, we get a more concrete description of this as essentially so T C tensor of C of R is given by T of R xy quotiented by x squared plus y squared minus 1 to x dx plus 2y dy tensored by R. But this really says that we have to impose that x and y has to be equal to a and b. So this turns out to be isomorphic to this one here. Oh, sorry, xy dx dy. Sorry, x dy. So this means that I have to impose the following equations. I have sorry, what am I doing here? R x y dx dy quotiented by x squared plus y squared minus 1 to x dx plus 2y dy, and then I'm imposing x minus a and y minus b. This is what it means by tensoring. But this means that x has to be equal to a and y has to be equal to b, which means that now x and y are fully specified. We already know that a and b have satisfied this equation. So this goes away, so this becomes r dx dy and becomes 2a dx plus 2b dy. Okay, now let's try to actually compute a concrete example. Let's now take R, real numbers, which means that now multiplying by, like, we can simplify this 2 essentially, because now we are knowing perfectly C2 for sure. So we can revise them here as R dx dy quotiented by a dx plus b dy. Now, let's take a point AB on the circle, which would be, keep a point on the circle. That is not, maybe let's do this simple one first of all. Let me just do, for example, this. So 1, 0, okay? The circle is here. I'm gonna do a mistake for sure. So 1, 0 is gonna be here. Is that right? Yeah. Okay. So if I impose 1, 0 in this equation, I have 1 and 0. I only get a dx. So I'm saying that dx has to be equal to 0, which is exactly this. Okay. Now we have to be a little careful because it's actually not dx. We have to like translate a little bit, right? Because it tells you this is gonna be a tangent thing. So it's gonna be tells you the tangent of that. So it's really have to be shifted to that point. So you can interpret dx as x minus a. Okay? And this way it gives exactly
That part is geometer's intuition, right? Because it's no way those computations tell you that they have to shift something.
It's just because this one here tells you the derivative, right?
Yeah.
So the derivative doesn't tell you where the point is. Now let me give you maybe another example.
We said we have to make that 0, right?
B goes to 0, right?
So you originally have a plane, and then you're quotienting out by making something 0.
Oh yeah, dx is 0, so
Yes.
dy is 1, I guess.
Dx. Oh, sorry.
Yeah, that line is dy. That line is what
I mean-
by quotienting out by dx.
Yeah,
But a is 1, b is 0, so you end up pushing it out by 1 times dx plus 0, so it's dx becomes 0, and you're left just with r of dy.
Yes, that's right. That's right. Sorry, I haven't done it all fast. So if I put this one here inside, that's right. I get dx dy quotiented by dy.
Or
That's right.
by dx.
Dx. You're right. By dx. You're right. Sorry. And this gives me exactly r d y. You're right. Sorry for that. Yeah. Sorry. I was going a little bit too fast. If I do the other one, of course, if I do 0, 1, for example, it's going to give me exactly dx.
Also, I think it does make sense to shift it there because we're taking the tangent space at that point.
Yeah, that's why I'm saying
Yeah.
that you're supposed to shift this.
But still, although we draw it like that, we do think of these as sub-vector spaces, so they aren't actually shifted.
Yeah, you're already at the point. That's the point. So now let's try to do something here. Can you give me an example here?
1 over root 2.
Over 2 and 1/2. Is that right? Is that correct? I'm forgetting my trigonometry.
Yes.
Pi over 3.
Yeah. So it's gonna be here, right? Okay. If I do this, I just have to put these numbers inside, right? So again, r dx dy quotiented by this plus 1/2 dy. And now I can essentially, so these I have two variables, I have one equation. So this is going to be isomorphic to r, let me call this one here, just z. It's going to be one-dimensional again, but this isomorphism tells me how to translate dx and dy using this equation, which imposes exactly the equation of the tangent line, which gives you this. Please don't make me do that right now. But this makes sense, right?
So the line you originally had, the one that connects with the origin, right? You're killing that line. So the whole plane will squash to that tangent line.
Yeah, that's right. Okay, I want to give you another example that is very interesting because it really shows you how much you can do, I think, with tangent calculus.
Sorry, can I?
This is somehow very similar to, yeah.
Sorry, I just want to ask that at the top there, the TC tensor CR. It doesn't seem like there's any information about A and B in that expression, and then
That's the point. The point is that R is an, so
A
R
comes from the diagram.
is a C module. From the fact that using this map here, which is going to be AB, you make R into a C module. So when you're taking the tensor, you have to portion by, the tensor will impose the equation that if you have something, if you have A tensor, let me do this, you have that if I do A dot B tensor C has to be equal to B tensor A dot C. And this translates into imposing the equation of A and B, x equals to A and B equals to B. So the information is hidden in the fact that R is a C module, becomes a C module.
So the map going out from C to R, because C is quotient of a free algebra that has two generators, X and Y. The map going out of C to R given by two elements of R. A and B are the place where X and Y map to by that map.
I was just concerned that the notation doesn't seem to reflect anything about.
It seems that in this notation there is no A and B because I'm hiding the A and B inside of the action of C.
Yeah, it's like when people write a
Comes to the
pullback,
push-out.
they write an X with a subscript, the thing in the vertex of the pullback, right? But it actually depends on the maps to the pullback. But those are just suppressed in the notation.
It's this one here.
People are lazy.
This one, this
Yeah.
push out here.
It's not the first time in your young life you've realized.
Now this is really beautiful, I think, but it's not stupid. But in some sense, like you're doing exactly as in differential geometry. So can we do something a little bit more in this context? The answer is no. No, the answer is yes. So let me try to do this. Let me take these equations.
So can you first go there and then come back?
Okay. So now I'm going to call B for bow tie this picture here. Equation, because then you're gonna check it on decimals, and if you do it wrong, you
Lemniscate.
see I lie to you. So if I plot this picture here, this equation here, it looks like something like this. So what is the problem?
Well, the node.
Why is that problem the node?
What's the tangent space there?
What is the tangent space there, right? I have here one-dimensional thing. I have no idea what to do here, and I have one-dimensionals here and one-dimensions here. So what can I do there? So it turns out that this is a tangent structure. I haven't told you the order yet, but it still makes sense. So let's try to compute the tangent bundle functor and see what happens in the tangent space. So can you help me with t? So if I do t of this, what do I get? So I'm duplicating the map, the variables. Then I get the first one is going to be the same one. Can you help me with the? Can anyone do the of the relation? So what do I get?
2y dy minus 3
2y dy
Minus 3.
squared dx.
squared dx, and now I have 2 is going to be 4 x dx. Awesome. Okay. So if I do again the whole idea of taking a point, so let me call this one here, this point AB. And if I do here, I can show you that I'll give you. Let's do the whole thing. So I'm going to calculate now the TAB of this B. So doing the same process here, essentially what does it really mean? It means that I have just imposed the equation x equals A and B and y equals B. Okay. So this means that this becomes R. X and y are just imposed, so we have dx dy. This one is given because x and a and b are satisfying this one here for sure. And this gives me 2a dy, not 2b, sorry, 2b dy minus 3a squared dx minus 4a dx. Okay, so let's do now an example. Let me see if I go here, I should get. I'm really tired. So.
Do you want to do an example?
X
That's
equals
the
one,
self-intersection.
so
Oh, there. Right, minus.
It's going to be x times x minus 2. So this will be 2. Is that right? Minus 2. No, minus 2. Yeah. Is that correct?
Yeah.
It's going to be 0 minus 2. Okay. So if I do this and I impose now a equals minus 2, 0.
Oh, yeah.
So a is going to be minus 2 and b equals 0. And post this equation here. What do you get? You get r dx dy. So b goes to 0. And here I have just a number. So it will be some number. N dx. Some number n. But the point that I want to make here is that this is going to be isomorphic to y. So this is one-dimensional. Get this. What happens when I do now the 0, 0 case? If I pose now a equals 0 and b equals 0, so I'm here now, I get that b goes to 0, a goes to 0, and a goes to 0. What does it mean? It means I have a two-dimensional thing because I have no equations on dx and dy. So what do I get is that t of 0, 0, b is actually r dx. Wow. So this is a new thing because this shows that we still capture some geometry done in tangent categories, but now we in a point where we have essentially a discontinuity, right? We have 1, 1, 1, 1, and it becomes 2 all of a sudden. Now the reason why that is possible is because in this category we have some special objects that are called infinitesimals. The idea is that we can somehow have fictional directions. So I can create the directions here somehow. Like I can have this. I'm not sure if I can specify that very well, but it is that we have some special objects. We call them maybe exactly our x quotient by x squared. And so if I look at this, if I look at this object here, and if I look at a point, I only have one point, right? Because this sends x to well, something such that a squared has to be equal to 0. But this is just going to be 0, so I only have one point here. However, this is not a point. It's not just R. This is not isomorphic to R. This is because this object here is actually, if you write it in here as the elements of this algebra here, actually given by A plus B, and call this here maybe R and S, R plus S epsilon, where epsilon is a new variable that squares to 0. So something that squares to 0, somehow you can think of this as like you're expanding something with Taylor, and you're killing all the terms that are above there, which literally means that you have something that will be the first derivative. So somehow you have an infinitesimal here. You can think of this as like infinitesimally thickening your space. You have a point. Geometers like to do this. They have a point and they drag a little thing around, like a little like fat point, they call it sometimes. So the fact that you have something like this somehow gives you access to as it was the space. It's not just a point, but it's something a little further outside of the point, which allows you to have dimensions, directions that don't correspond to actually physical. They don't correspond to points, which is why you have this special possibility to have these things that can blow up in dimensions. That's my understanding of those kinds of things.
Is it wrong to think of it as you have like directions, a choice of tangent here and a choice of tangent here, and the product? Yeah.
To me, this translates into say that here I have no idea where to go.
If there were three intersection had 6 rays instead of 4.
Like a rose or something.
It'd still be.
It'd still be
It will be two
Would it still be
dimensional.
two-dimensional?
It can't be more dimensional than like the ambient space here.
It's not that you have no idea where to go. You could go in a linear combination of 2 independent directions.
Yeah, exactly. Like to me, it feels like this. In differential geometry, I always want to be sure that I have exactly the directions I can move on. So if I'm moving physically in the space, I will have corresponding directions. But in algebraic geometry, you have the possibility to say, if I arrive at a point where I have 2 choices, I have to include all the possible choices that I have generated by those 2 directions. So you're saying like, okay, I don't know what to do here. I can go all around somehow. That's what would be.
It corresponds to saying that any line passing through that point is a line, right?
Yes. Yes. It's embedded in the tangent space. It's a subspace. It's embedded in the tangent space.
So this is very elegant, but like the algebraic geometers know this already. This is the Zariski tangent space, right? So what your formalism is bringing, you need to explain what more it's bringing that they didn't know already.
That's true.
Yeah.
That's a good point.
Yeah.
So I don't think we are there yet.
But doesn't need to bring something new, or can it just say, well, these things they did in algebraic geometry, which they were doing by a weak analogy, is now exactly a consequence of the same theory that works in differential geometry?
The new thing here is that we are doing it very much just using the language of tangent categories. These are just like exactly the concept they're using in category theory and in tangent categories, and they bring exactly the concepts that they have, the algebraic geometers have. So this doesn't mean that we're doing new things. There's very much nothing new here. Like algebraic geometers have done this like many years ago.
So differential geometry, what differential geometry does and what algebraic geometry does, before was just an analogy, but now it becomes formally the same thing.
Yeah. That would be essentially the
Yeah, well, I don't know. I would say that this was sort of understood. I think it's when you start getting to those lower things there that becomes more interesting. Like you're still at 0.1. I think those number 0.4, 5, and 6, it would have been a little bit more obscure.
I'm gonna tell you what the structure is.
Yeah.
Yeah. But to be clear, like what like this is a very new thing. Like it was like this. What I'm showing here is what Jeff Crocker like essentially explained to me and found like I think it was like 3 years ago, something like that. And from there, people started to find things. But for now, the research that we have at this level is to like try to see what the concept we already have in tangent categories correspond in the concepts on the algebraic geometry. And so far, they fit very well. Are we finding something new? Not yet for now. And it's not anything surprising. But it shows that tangent categories. I think that to me, the take that I want to give you is that it shows that tangent categories are a strong language for geometry in a more general sense, both in algebraic geometry and also in differential geometry, and also possibly new things. Okay, so maybe I should tell you now at this point, should tell you what the other structure is. Okay, so P is, as I said, goes from A to T of A. It sends A into A. Z goes in the opposite now, goes from T of A into A. So TA is denoted by A and dAs. Can you guess what Z does? Yes?
And dA to 0 and A to A.
So A to A and the vector to 0. That's right. The sum, we have to understand what the sum is. The sum goes from T of A into T to A. T to A is the pullback of the projection along itself. Opposite category, push out. So this really is TA tensor over A of TA.
I think over there it's written the other way around.
Yes, because you're in the opposite category. So I'm writing now things as it was in CLR because it's just a panic, the idea of like looking at that in the opposite category. So A goes always in A. Here this also has an A. What about DA? Do you have any suggestion? You guess what that A would be, DA would be.
Just A tensor dA plus dA tensor A or something? No.
Not exactly. So it would be dA tensor 1 plus 1 tensor dA. The lift goes for now TA in TA. So the T takes, so TA contains A and dA. These are the objects, the elements of this. I have to apply T of this. We should have another D. I call this one D prime. So I have D prime A and D prime DA. So L goes like this. Sends A to 0 to A, DA and D prime A to 0, and DDA into DA. And finally, the canonical flip goes like this. A, DA, D prime A, D prime A. This goes into A. DA goes into D prime A, D prime A into DA, and D prime DA like this. So it flips this two.
I just want to make sure. A in S, A is supposed to go to A. We're not duplicating A. It's not A tensor A or something like that. We're just doing.
Yeah. Well, really, you're tensoring over A, right?
Oh yes, which says the same thing.
You have a copy on A here, and then you're like
Yeah. Sorry. Yeah. So it says the same thing as just copy.
you're gluing them together. That's what the push out does. Okay, so this is the structure. It's not very.
Sorry, Marcello, should it be D prime DA on the right hand side as well, or DD prime?
Over here.
Yeah.
I guess
Yeah,
it depends how
yeah.
it depends if it's the same generator.
It depends on how you write the things. If you think about this as D prime, this if you want like this, I'm not sure. The case will be yeah.
Not true. What? How?
I think that would be like the best convection we have. Yeah.
I think it should
That's how you understand it. But I think about this as generating the same symbols, it flips the two. Okay, so what time is it right now? Sorry. I want to be sure that
Quarter past 3.
have time to tell more things later. So I would like to just mention one final thing. So how did people came up with this idea? So it's not exactly obvious where this come from. Like, I mean, it's not for me, but Graham actually suggested something. He suggested that T is actually left adjoint. Is that what it is?
Yeah.
Okay. Of R epsilon tensor blank, where R epsilon is something here. Okay. I don't know if you remember, but last time, in the last minute, I said that P alg R is also a tangent category. It has this tangent structure here, where the tangent bundle functor tensors by R epsilon. So the categorical community of R algebras has a tangent structure. So one of the first results that Jeff and Robin proved is that when xt is a tangent category and all the Tn is going to be the n-fold push out of the projection of itself, if you remember. All of them has a left adjoint. Sorry. Then x opposite t opposite is a tangent category where t opposite is given by the left adjoint is the left adjoint of t. Okay, so maybe I should use another thing. Maybe I'm using a circ. Okay. So the idea is that when a tangent category has the property that all the tangent bundle functor and all the Tn, which is that these n-fold pullbacks, admits left adjoints, then you can dualize the tangent structure. And the opposite category has tangent structure, but the tangent bundle functor is given by the left adjoint over here. Moreover, because now you're in the opposite category, now the tangent bundle functor also has a left adjoint, right? Because left adjoint and right adjoint goes the opposite way in the opposite category. So this is also dualizable, and the dualization of dualization is the original category, is isomorphic to the original tangent category. So we have essentially a way to sometimes to have the dual of a tangent category. It's very important though that this condition is satisfied. It turns out that, as I said, this is a tangent category, and the tangent bundle functor is given by this. But the one that I told you before, this T omega of A, which is given by the symmetric A algebra of the modular curve differential, is precisely a left adjoint of T epsilon. It turns out that also all the n-fold pullbacks have left adjoints. You can prove that because the category is complete. So because of this, you have essentially that the opposite category of this is a tangent category, and is given exactly by this tangent bundle functor. But this is very interesting because this tangent structure here is way simpler to describe than this one here. So when people realized that, they knew about this, and then they dualized it, and they found the description of this. We now had to check that those maps are defined and blah, blah, blah. So this is essentially the abstract reasoning that there is here. And it really shows how the categorical approach to geometry is very helpful here, because we are using just like some tangent categorical techniques to construct the tangent structure on the opposite category. Okay. Does anyone have any question about this?
Yeah, I mean, you can do it that way if you're an algebraist, but if you're a geometer like me, you would say, you do it, you start from the other direction. You say, what do I want a tangent vector to be? And then you say, well, a tangent vector should be, I know what that should be. And you say, well, that should correspond to a hom out of this thing into my space, and that'll then allow me to construct that thing. So, you know what I'm saying?
Yeah, for sure, for sure. Both directions are same.
Equivalent, but it just depends where you start.
It makes sense. But I don't think it's very easy to construct all of those.
I think you could. I think
of course you can do that.
Yeah.
But yeah, that's like, I guess, a different perspective. Yeah.
Do you just need the left adjoint or also the place where the rest of the structure?
So the left of the structure is essentially given by mates. You're using mates, and it gives you exactly the structure.
Yeah.
What is not obvious is that mates also preserve, those mates preserve the limits that you need.
So it's, when it has a left adjoint, you get the thing. If it has a right adjoint, then it's nothing. Or do you also get something?
No, I don't think that the right adjoint gives you anything interesting. One important thing is that differential geometry, the tangent factor does not preserve all the pullbacks, which means it's not going to be a right adjoint. So you don't have a left adjoint on differential geometry. So this construction doesn't translate into differential geometry. And it's actually very important there because the point is exactly that we don't have these infinitesimals. So maybe I can also say that. So one other way of thinking of this is that this tangent manufacture here can be understood as the exponential object of in the category of C algebra opposite of R epsilon. So in C R opposite. So you can think of this as the internal home in this category though of this. Okay. So So sometimes like you have these infinitesimals here that allows you to have things that are too nice for differential geometry. Because the spaces are nice in differential geometry than in algebraic geometry. You have pathological things like this in algebraic geometry. Okay. What time is it? Do you maybe want to have like a little break or? Okay. So now let's talk about a few things that are more like they're part of the theory of tangent categories. So like we have the different directions in which the theory is developing. And one of the direction, probably like one of the biggest like fields of research that we have done so far is to take constructions in differential geometry mostly and to translate them internalize that into tangent categories. Like in differential geometry, we have like many geometric constructions. We have to understand them from the point of view of tangent categories, and we have to understand what they are in that context. So the first thing that people looked at is vector fields. So vector fields. Bruce coming back because he asked me like many times about vector fields.
I think you should be coming back. Yeah.
Okay, so maybe I can tell you what a vector field is in differential geometry usually. So the idea is that if I have a space, a smooth space like this, I want to assign to every point a tangent vector at that point. So I want to have at each point I have a special tangent vector that I'm picking out of that, and I want that assignment to be smooth. You think of this something like this. You can think of this like a flow of arrows that essentially distributes along all the space. Now, vector fields are very important in differential geometry, but I don't know what your background is, but if you've ever done anything about ordinary differential equations, these are ordinary differential equations. They are ordinary differential equations because an ordinary differential equation is a way to tell you at every point, right? It tells you where to go and at what speed. Okay. If you integrate that equation, it literally means that you start at a point, so you have an initial condition, and you navigate your space following the direction of this point and at that speed. So this literally is a roadmap. It tells you where to go and at what speed. Exactly. So integrating this, it literally means that at a point, I'm following these lines and so on. This actually is called the integral flow of the tangent of the vector field. Okay. And clearly they're very important. So how do you axiomatize them in tangent categories, or actually in differential geometry is already done that. So the idea is that if you want to assign for every point tangent vector in a smooth way, is the same as taking a section of the tangent bundle. The tangent bundle lives here. it's a space that lives above, like it's like a bundle over this, and we have a projection. Remember, the projection takes a tangent vector and it sends to its base point. So if you think about T of M as something like this, taking a section of the projection, it means essentially doing, you imagine like taking a knife and cut it along the space in this way. It could be something like this. This is what they're called sections. Now, this means that at every point, right, this is going to be a tangent vector at a point. So at every point, you're associating a tangent vector. So over this point here, you're giving a tangent vector, which corresponds to that value over there, and so on and so forth. So we think about this in the following way. We say that a vector field, the definition, a vector field on M is a section of P of M, which means that it's going to be a map that goes from M to T of M, satisfying the following condition. So I think of this in the following way. I take a point X, and I send X into something here, and this will be something like X, and will be like a Y, sorry, and a U, and a V, right? But this assignment needs to satisfy the following condition. If I project down to P, this one here to M using P, this sends this one here to Y, and I want to say that Y has to be equal to X, which means that this map is sent into X into something XV, which literally means a tangent vector at X. Okay, so that's what a vector field is. And this is literally the definition in tangent category. So if you have a tangent category, you have an object, a section of the projection is a vector field. Now, one of the crucial results that people proved in differential geometry is that vector fields over an object over a manifold form a Lie algebra. I don't remember the definition in differential geometry of the Lie bracket, but the idea is that they use differentiation and like essentially, my understanding, a vector field, there's a way to relate vector fields to derivations, and derivations form over the time a Lie algebra, and the Lie algebra is exactly the Lie algebra of vector fields. So we would like to somehow, so we want to show that vector fields in tangent categories form a Lie algebra. So incredibly, this result was actually done by Ruzitsky in his first paper, 1984. But I think I mentioned that he actually wrote the proof in 40 pages in Czech, and no one really, outside of him, I guess, really read those notes. So people had to reprove that. And in 2017, if I remember well, Crockett and Crockwell we consider that problem and actually gave an entire proof, and it's one paper. It's not very long, it's like 14 pages, something like that, but it's one paper only for one proof. I'm going to show exactly. I'm not going to do the proof in any possible way, but I'm going to show what is the equation that they prove. So here's the idea. We would like to define if you have U and V from M n, I need to define a few operations. The first operation I have to define is a zero operation. So zero operation. We want to have a zero vector field. Okay. Second, I want to be able to take U and V and sum them together. 3, I want to be able to take two vector fields, take Lie brackets of these two vector fields. And Lie bracket is the binary operation. Okay. So so let's introduce zero and the sum first. So can you guess what would be the zero with the zero element. So I'm taking VF X M X T M. The set of all the V's vector fields. So can you guess what would that be the zero element in this set, in this algebra?
Be the thing that assigns the zero vector to every point.
Yeah, so we already have always a vector field, which is a zero vector field. This is part of the axiom of a tangent category. So this will be our zero. What about the sum? So I am going to take U and V now. It goes from M to N, from T of M. And I'm going to do the following thing. U plus V given by, so here I'm taking the pullback of the P along itself. And I can use the universal property to construct this map from U to V. Now I'm going to take the sum like this.
Sorry, Marcello, we have a problem with the camera.
Oh, sorry.
Oh
yeah.
it's not my fault, but yeah, if you can wave your hand and then it's gonna be fixed. Maybe. Okay, great, thank you. Sorry.
Working now?
Yeah.
Sorry for that. I really like that spot. So what does it? How do we how do we define this? Well, this is the pullback of the projection along itself. So you have M. I'm going to go with U. I'm going to go with V. But UP is identity. VP is identity. So I have a unique morphism here, and we're going to give you by U and V. Okay. So I have this morphism here, and then I use the sum to sum them together. So if you think about this in terms of like pointwise, so using our notation, this sends X into X, UX, and VX, and the sum sums them together. Okay. Now, using the fact that this is associative, commutative, and unital with respect to the zero, we already have that. So from here we have lemma VF V the zero with the sum is a commutative. And the proofs essentially uses the fact that the sum is unital, commutative, and associative. And the unit is going to be given exactly by the zero. So the next step is to like add this Lie bracket construction. And this is really the hard part of this construction. To do that, the first thing is that we need to add negatives. So definition, I think I said that, a tangent category has negatives when we have an n natural transformation from T of M to T of M, naturally in M, such that essentially we already know that the fibers are commutative monoids. We're going to make that into an abelian group. So we have the possibility to take a tangent vector, and I have also the one that goes back essentially. So the idea is that such that we write this down. So this will be identity and negation. Sorry, negation. E2. If I go down with the zero, if we take a vector and its negation, and I sum them together, I get zero, which means that I have to go down with P and with the Z. Okay. So here I'm literally saying that. So n can be understood as taking x u in x minus u. And so this tells us just that u plus minus u is just equal to 0. That's the equation here. Okay, so now that we have negatives, we can construct the following morphism. So take u and v, vector fields, and define the following map. So we're taking TV composed with u. This goes from M. First, it goes with u in Tm, and then we're going to take T of V, Tm. we can also take this map CM composed with TU composed with B. It goes like this. It goes from V first, E of U. Remember that as part of the axioms, we have this canonical flip, this symmetry here. So the idea here is to say that we want to take this map minus this map. So minus, it means that this will be T of something. So when I have F and G's, and it goes from M to T of N, I can write F minus F plus G to be this, such that, sorry, F followed by P is equal to G followed by P. So this will be T to N, sum over N, to be F and G, and do this. F minus G is given by essentially F plus negation over N composed with G. Okay. If this notation makes sense, I can now write the following construction. So I'm going to write TV goes with U minus CM U goes with V. This is a map that goes from M into T, T, M. Now notice how much stuff we're using. We're using the projection sometimes because, well, these are vector fields, so these are sections of the projections. We're using the zero in that structure over there. We're using the sum to construct sums here. We also need to use negations. Okay. Now, what I would like to do is to have an operation that takes me U and V, and it gives me a new vector field. This has to be a vector field. But what I'm having here is something that goes from M to TM. So how can I somehow get what I want? Well, what haven't I used yet? P is part of the is the fact that U and V are vector fields, so I use them. Yeah. C. Or in the axioms I gave the canonical flip, the vertical lift. Sorry, we haven't used the vertical lift yet. I also have used C over there. So the universal property of the vertical lift also tells us this: that if we constructed this special map that I call C, such that this is a pullback diagram. Okay. So this was the universality of the vertical lift. So here I'm starting with something that goes like this, and it goes here, and here I can just use the identity. Now it will be map P, B, comma U. Okay. And it turns out that if you do the math, these commutes, which gives you a unique map over here. Okay. So let me call this one here map B. Let me give a name to this map here as follows. This special double bracket. Okay. So we have double bracket here. And this gives me this double bracket. Okay. So here I'm going from M to T2M. So I simplified a lot, but it's not done yet. The final thing you have to do that the D bracket is actually defined to be M to T2M double bracket tilde, and now we're going to use pi 1. Now, the theorem goes as follows. Theorem First of all, we have that uv is a vector field. Two, uv plus vu 0, 3, this is the Jacobi identity. This is the antisymmetry. And together, this shows that particular that BF is the algebra. Now, you can clearly see that this equation is not easy because it involves three things and sums and so on. Like, I mean, I don't know if you've ever seen this one here before, but this is kind of like a weird version of associativity. And this is clearly the hard part of the proof. And that's why people spend a lot of time to prove this one here. That was not easy to prove. And I'm not going to show this, but it turns out that this result is true. And so we have this amazing result, I think, because it really is a very structural construction of the vector field, this structure. It shows you that vector fields in a tangent category with negatives, and it means a Lie algebra, like have a Lie algebra structure, which is, I think, is amazing because it really shows what, I don't know. We're not using points. There's nothing here. It's crazy. Like, it's crazy that you can do this. But notice how we use literally every structure here. We use the projection, use the zero, use the sum, use the negatives, use the canonical flip, and finally also the universality of the lift. So this is like really like something that tells you that vector fields, this Lie algebra structure is very geometric. Like, it tells you everything. You have to use everything there somehow.
When you just define vector fields in the normal way, is there a canonical way to turn that into Lie algebra?
Yeah.
I mean, you can do this, for example.
Like, no one did that before. In differential geometry, the point is that you have points, right? So the idea in differential geometry, the proof goes as follows. So vector fields.
Marcello, sorry, once again, can you maybe?
Yeah. So in differential geometry, first, people proves a very important result that shows that every vector field is in bijection with derivations over C infinity m. Okay, so these are derivations with this. There's a correspondence between these two concepts. Now, derivations form a Lie algebra canonically. So derivations, if you have a derivation 1 and a derivation 2, you have d1 and d2, two derivations over a commutative unit R algebra A. Then the Lie bracket is given by the commutators. So this will be d1 comma composed with d2 minus d2 composed with d1. Okay, so this is like a very standard thing in for derivations. And now you have a new derivation. And so you have, instead of two vector fields, you construct the corresponding derivations. You get the Lie bracket of these two derivations, and you go back to a vector field. That's one way of doing it. And it turns out that you can actually express that in a very concrete way with points and as a functions and so on and so forth. So this is essentially the idea in differential geometry. But this is a very more structural thing because, like, you don't involve anything like this here. So the question now is, what are vector fields in the examples? So of course in differential geometry, so examples 1 in differential geometry. So in SMAN, maybe in the category of smooth manifolds, is exactly what you expect. So the bracket of vector fields is equal to the bracket of vector fields. So this will be the tangent structure, and this is the usual one. So this captures exactly the usual one. What about algebraic geometry? Okay, so e.g. in C alg are opposite. So in C alg are opposite. First, we have to understand what vector fields are. So remember that the projection is something that goes from A to T of A in C alg R. Right? And this sends A into A. So vector field has to go from TA in A. And this is fully specified by assigning A to something, I call this unit B1A, and DA to something. Let me call this unit B2A. Yeah. But we have to impose an equation. We have to impose that V has to be a section of the projection. And we have to be really careful here because we're in the opposite category. So this actually is a retraction. So this means that if I do first the projection, then I take the vector field, this has to be the identity. So here I'm sending A to A, and this one here sends into V1A. So what I'm saying is that V1A has to be equal to A. So a vector field is fully specified by a map of this type, sends A to itself, and dA to something like this, a new map. So in particular, we can define now this map here. It sends A into V of dA. Right. This is the map that I'm defining here. So remember the properties of D. D satisfies the following equation. So dRA plus SB has to be equal to RDA plus SDB. And D of AB is equal to ADB plus BDA. So let's prove that this one here is a derivation. So we take RA plus SB, this is sent into V of D RA plus SB. And this is given by V of RDA plus SDB. But be careful because I'm specifying V. I'm saying that V is the unique map fully specified on generators as follows. So defining this on generators, it means that it distributes along the generators here. So here will be exactly R, B, D, A plus S, B, dB, but this is equal to R delta V A plus S delta V B. And similarly, you can show the following things. So if you do this, this gives you D. This is equal to A dB plus B dA. And I'm using the fact that this distributes on the generator. So this gives you A, because VA is equal to A, plus B dB plus B B dA. So this gives me A delta B B plus B delta B A. So what I'm concluding here is that vector fields are derivations. And moreover, if you have a derivation, you can put the delta here, the derivation here, and you construct a vector field. So derivations are in the sense of this correspondence, vector fields. Remember that we started by saying that the modular current differential is the universal A module with the universal derivation. So of course, these will capture derivations. We literally put the derivations there. So now we have this interesting thing that tells us that vector fields in the category of algebraic geometry, gives us of affine schemes, gives us exactly derivations. Now you can wonder what would be the algebra of two vector fields. Well, this will be corresponding to exactly the commutator between the derivations. We have a clear picture that vector fields, again, they both generalize vector fields in differential geometry and the one in algebraic geometry. What time is it? I think that I'm kind of done.
You have 1 minute left.
I have 1 minute. Okay, so let me wrap it up a little bit. So we talked about tangent categories, and there's too many things that I wanted to say, but really that's enough for now. So in my notes, if you haven't done, I hope you can. I put some more things. So vector fields are only one of the constructions that we do, and it's the first construction we did, but there are many others. And in particular, people started to define Euclidean spaces in a tangent category. They're called differential objects, and they also generalize vector bundles. Vector bundles are those in differential geometry are maps like this with some nice properties, such that the fibers are vector fields. And these are vector spaces, vector spaces. These are very important in differential geometry. They are like fundamental in physics. Like if you do any physics, be like mathematical physics, these come all the time. And so we have now a definition of in tangent categories of vector fields. They're called differential bundles. Vector bundles. Sorry, they're called differential bundles. And we know that in the category of smooth manifolds, maybe I say this. So differential bundles. We do maybe a little like table. So differential bundles in SMAN, they correspond exactly to vector bundles. And this is a very non-obvious statement because differential bundles, you don't talk about the topology. Vector bundles are all about topology. And in C-alg R opposite, they correspond to modules. Those are very important because algebraic geometries always work with modules as vector bundles. People also like generalize another concept that is connections. Connections are very important in differential geometry, but they're a very hard concept, and I find them very hard. It's a way to say that you want to take the derivative of a vector field. And if you want to take a derivative of a vector field, you have to take into account the fact that the space might not be flat, it might be curved. And to do that, you need to have a special object that is to a connection. And from the connection, you have concepts like curvature, torsion, others, and those are like fundamental everywhere in differential geometry and in physics. Like general relativity is the theory of connections in disguise. Like these are very fundamental concepts. And in SMAN, they correspond exactly to connections. And in C-alg-R, there's also in algebraic geometry, there's also a notion of connections on modules, and they correspond exactly to connections on modules. These are connections on vector bundles. But now Jeff and I are working on a more generalized version of connections on submersions. We have a lot of things that are doing. So like one big active part of our research is to take a notion in differential geometry usually, generalize to tangent categories, and then see what happens in other contexts like algebraic geometry. So my research specifically, I couldn't talk about this, but went into other directions. So for example, I extended algebraic geometry, what I've done here, on things that are not necessarily commutative to unitary algebras. There is a notion of operands, which is a way to parameterize algebraic objects. Every opera gives you a type of algebra, essentially. So for example, Lie algebras are an algebra over a specific operand. Poisson algebras are another type of algebras over another operand. Commutative unitary algebras are algebras over an operand. Okay, so those operands parameterize algebraic objects. And for each of them, I constructed two tangent categories of P-alg R and also P-alg R opposite, which is very interesting because this generalizes what we've done in algebraic geometry to other contexts. For example, in non-commutative geometry. There are many directions in which we are going, and yeah, so that's it. I think that's probably enough.